Welcome to the CyberArk Sentry training program, where we will translate complex architecture requirements into the practical skills necessary for your certification. This introductory chapter lays the foundational roadmap for mastering the PAM-SEN exam blueprint through technical excellence and strategic implementation. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to CyberArk in any way. All trademarks belong to their respective owners. This content is for informational and educational purposes only and is intended to assist in exam preparation. It does not guarantee certification or official endorsement. In this course, we are going to deconstruct the CyberArk Privileged Access Manager ecosystem to ensure you are ready for the Sentry-level assessment. Whether you are a system administrator, a security engineer, or an architect, this curriculum is tailored to align your existing knowledge with the specific technical demands of the certification exam. We will cover the entire scope of the product lifecycle, from initial vault deployment and infrastructure configuration to advanced session management and diagnostic troubleshooting. You will learn not just the how, but the underlying mechanisms that govern these systems in high availability environments. By focusing on the structural integrity of your deployments, you will gain the ability to pass the exam and effectively manage complex privileged access scenarios in the real world. Our study plan follows a logical progression that mirrors the architecture of a production-grade CyberArk environment. We begin by establishing the Enterprise Vault, where we address virtualization requirements, Windows Server baselines, and the critical networking configurations that dictate Vault connectivity. From there, we move into the integration of web interfaces, load balancing, and complex authentication flows, including SAML and multi-factor authentication. As we progress, we investigate the policy engine and session gateway infrastructure, which are central to automated credential management and secure remote access. Understanding these distributed components allows you to design scalable systems that satisfy the rigorous security governance mandated by the Sentry exam. The latter part of the course focuses on the operational reality of managing these components throughout their full lifecycle. We will explore best practices for patching, certificate rotation, and database maintenance to ensure your PAM installation remains secure and performs at its peak. Furthermore, we will dedicate significant time to diagnostic frameworks, teaching you how to analyze logs and connectivity patterns to resolve failures before they impact production. This systematic approach ensures that you are prepared for both the theoretical questions on the exam and the performance-based configuration scenarios. We will establish clear benchmarks for your knowledge validation, helping you identify areas that require additional focus before you schedule your sitting at the testing center. Finally, we will examine the administrative policies and maintenance requirements that keep a mature, privileged access management program functional. You will learn how to articulate the benefits of the Sentry credential and how to maintain compliance with CyberArk's specific architectural standards. Throughout our time together, we will treat the system as a collection of specialized services that require careful orchestration rather than a collection of separate tools. This shift in perspective is the key to successfully navigating the exam and establishing your credibility as a senior practitioner within the CyberArk ecosystem. We will maintain a rigorous, fact-based focus to ensure that every minute of your study time contributes directly to your mastery of these components. I look forward to our progress through these technical modules. Welcome back. We are now moving into the standalone digital vault installation, which serves as the foundational bedrock for any secure CyberArk implementation. Installing a standalone digital vault begins long before you trigger the setup executable. You must ensure the Windows Server operating system adheres strictly to the hardening requirements specified by CyberArk, which necessitates a clean, dedicated server instance. During the initial planning phase, you should define the file system layout carefully, separating the operating system partitions from the data storage drives where the private ARC database files will reside. This separation is not merely a suggestion, but a critical architectural requirement to ensure that disk I/O demands of the vault do not conflict with the operating system processes. Before mounting the installation media, verify that all hardware controllers and storage volumes are recognized by the operating system kernel and that the NTFS permissions are inherited correctly. I find it useful to document the drive mappings early, as these paths will be requested multiple times during the configuration wizard. Taking the time to validate these underlying requirements prevents the common pitfalls of corrupted database initialization or incomplete folder structure generation during the primary setup phase. Once the server environment is verified, you execute the installation binaries, which initializes the core Vault services and the underlying database engine. When the installer finishes, the immediate next step is the execution of the server hardening script provided within the software distribution package. This script is essentially a collection of security policies that strip away unnecessary services, disable non-essential protocols, and tighten the Windows registry settings to create a minimalist, hardened environment. It is imperative that you do not manually interfere with these settings afterward, as the configuration is calibrated to provide a specific security posture. You should verify the installation by checking the directory structure against the expected CyberArk schema, looking specifically for the presence of the data, system, and logs directories in their designated locations. If the installation was successful, the Vault services should be in a stopped state until the initial configuration utility, often referred to as the server setup, is run to define the primary Vault properties. The configuration utility is where you define the cryptographic properties that serve as the security perimeter for your secret storage. You will be prompted to manage the master key, which is the root of the Vault's encryption hierarchy. And typically, you should handle this using physical tokens or other secure storage media provided during the deployment process. The master password must be stored in a separate, highly secure location, as its loss renders the data in the Vault permanently irrecoverable. Following the cryptographic setup, you configure the secure administrative interface, which ensures that only hardened administrator accounts have the capability to interact with the Vault's internal database. At this stage, you also confirm local policy restrictions, such as limiting network access solely to the specific IP addresses of anticipated Vault components like the CPM or PVWA. This phase represents the transition from a generic operating system to a specialized, hardened security appliance, and it requires absolute precision in every input. Post-installation analysis is the final, essential step to ensure the integrity of your deployment before moving into production networking. You should check the basic service states using the Computer Management Console or the dedicated CyberArk Service Monitor tools to confirm that the Vault server service, database service, and related drivers are running. If a service refuses to start after a reboot, the error logs within the installation directory are your primary source of truth, as they will typically highlight permission conflicts or missing dependencies. A common mistake is failing to verify the database operational structures, which can lead to intermittent performance issues or cryptic error messages when later trying to create safes. If you encounter issues with the setup, you should perform a systematic audit of the hardening logs and ensure that no other security software on the network is blocking the local interface traffic. Maintaining a clear log collection process during this phase is the best strategy for troubleshooting connectivity errors that often appear when the Vault first tries to communicate with external components. See you in the next lecture. Welcome back to our exploration of CyberArk deployment architectures. Today, we focus specifically on the implementation and operational mechanics of high-availability Vault clusters. In an enterprise environment, the Vault is the single point of failure for your entire privileged access management strategy. To mitigate this risk, we deploy digital vaults in a clustered configuration using Microsoft Cluster Server Architecture, which relies on shared storage to maintain state. The fundamental premise here is that only one node in the cluster, the active node, holds the service locks and manages the data storage at any given time. If the active node experiences a hardware failure or a service crash, the passive node must be capable of assuming ownership of the shared storage and restarting the Vault services. This transition relies on the cluster heartbeat mechanism, which ensures that nodes are constantly communicating to detect potential outages. When the passive node stops receiving heartbeats from the active node, it initiates the failover sequence, promoting itself to active status to maintain service continuity. The configuration of these clusters requires meticulous attention to network interfaces and virtual IP mapping. You must define dedicated network paths for the internal cluster communication, often referred to as a private or heartbeat network, to ensure that cluster signaling traffic remains separated from the public production traffic. The virtual IP address acts as the gateway for all client and component connections, abstracting the underlying physical nodes from the Vault agents and the web interfaces. If your environment spans multiple subnets, Your design must explicitly handle the mapping of this virtual IP address so that it remains reachable regardless of which physical node holds the active role. Often, this requires coordinated configuration at the network layer to manage ARP entries or routing updates, ensuring that clients do not experience connection drops during a failover event. Storage connectivity represents another critical vector for successful cluster deployment. In a standard Microsoft cluster environment, we typically leverage fiber channel or iSCSI SAN technologies to provide shared storage volumes that represent the vault's data and metadata partitions. Before installing the vault binaries, you must successfully mount and validate these drive letters on both nodes, ensuring that the cluster operating system can effectively switch the drive ownership. The vault binaries themselves are installed locally on each node, but the configuration files and the data held within the safes are stored on the shared volumes. Consequently, the installation process requires you to initialize the vault in a way that points the service dependencies and resource logs to the shared disk resources created within the cluster manager. Monitoring the health of a cluster requires a deep understanding of heartbeat signals and resource states. If the nodes are properly communicating, the cluster resource manager maintains a clean status, but degradation can occur if network latency interferes with heartbeat intervals. We tune these metrics to balance between responsiveness and stability, preventing a scenario where a temporary network flicker triggers an unnecessary failover. Analysis of the cluster logs is an essential activity, as these provide the audit trail for resource transitions, disk ownership switches, and process terminations. When troubleshooting, the most significant risk is a split brain scenario, which occurs when both nodes believe they are the active member due to a loss of network communication between them. To mitigate the risk of split brain, we implement quorum configurations, which provide a tie-breaking mechanism when node communication is severed. A quorum witness, such as a disk-based or file share witness, allows the cluster to establish a majority vote on which node maintains legitimate control. In a two-node cluster, without a witness, the risk of both nodes attempting to mount the shared storage simultaneously could lead to catastrophic corruption of the vault database. Engineering the quorum correctly is therefore not merely a best practice, it is a fundamental requirement for the maintenance of data integrity during degradation events. When performing manual failovers for maintenance, always use the automated cluster management tools rather than manually forcing service restarts to let the cluster resource hierarchy handle the dependencies in the correct, predefined order. I look forward to our next discussion on architecture. Welcome back to our discussion on architecting robust systems. Today, we will examine the critical implementation details of CyberArk disaster recovery vault architectures and the cross-site replication topologies required to maintain service continuity. In an enterprise environment, a disaster recovery vault is not merely a backup secondary server, it is a synchronized shadow of your production environment that must be ready to take over at a moment's notice. The architecture relies on the Private Arc Disaster Recovery Service, or PADR, which operates as a Windows service on the DR Vault machine. When we configure this service, we define the replication parameters within the PADR NI file, which dictates how the DR Vault communicates with the primary vault. You should consider this file the nervous system of your DR strategy, as it stores the source vault IP, the interval between synchronization checks, and the essential timeout settings that prevent false positives during network instability. Configuring these parameters involves a delicate balance of frequency and bandwidth usage, especially when dealing with sites connected over wide area networks with limited throughput. The synchronization process itself utilizes a combination of full data replication and optimized differential sync operations to maintain parity between the physical vault databases. During the initial configuration, the DR Vault performs a complete transfer of the master vault's data to create a baseline, but subsequent operations rely heavily on transaction log shipping to update the DR site incrementally. You must monitor the PADR logs diligently, as they provide the truth regarding whether the replication channel is healthy or suffering from persistent latency. If the replication lag grows too large, the database synchronization will fail to reach a consistent state, rendering your DR readiness insufficient for a sudden production failure. Engineers often mistake high disk activity for progress, but efficient synchronization is measured by the delta of database logs rather than raw data throughput. When we simulate a production vault failure, we are essentially testing the integrity of the automated or manual failover transition. Successful drills require that you verify the target state of the DR vault after it has been promoted to the primary status, checking that all essential services are active and that the vault keys are accessible in the new environment. Post-failover recovery is arguably the most complex phase, involving the reversal of replication directions to ensure that when the original production node is restored, it synchronizes its state with the new master. Returning production workloads to their original location requires a methodical approach to confirm that no transactional data was orphaned during the switchover. You must pay special attention to the firewall requirements. Since replication traffic uses specific ports, any shift in IP addressing or network topology during a recovery event must be accounted for within your security connectivity profiles. Finally, let us look at the operational requirements for maintaining this environment over the long term. Analyzing replication lag is an ongoing discipline, as network congestion can frequently throttle the synchronization of critical security objects. Bandwidth allocation must be prioritized to ensure that the vault's internal database replication can complete within the RPO or recovery point objective, defined by your organization's business continuity plan. Connectivity profiles are often configured to allow multiple failover paths, but each additional path introduces complexity in tracking the master and slave roles within the replication topology. By strictly adhering to these architectural standards and maintaining a disciplined approach to logging and performance metrics, you ensure that the DR solution remains a reliable pillar of your security infrastructure. I look forward to discussing the next topic with you, so please join me there. Welcome back. We are now entering the chapter on capacity planning and resource sizing, where we will translate architectural requirements into concrete hardware and infrastructure specifications. Effective capacity planning for a CyberArk PAM environment is not about guessing. It is a rigorous exercise in dependency modeling and performance forecasting. To begin, we must formulate detailed capacity metrics that account for the reality of concurrent session volumes and the total number of managed accounts. You need to consider transaction frequencies for both automatic password management and active privilege sessions, as these drive the underlying resource utilization. Retention criteria are equally important here because the duration for which audit logs and recordings are stored directly dictates the cold storage growth rate. By mapping these activities to a timeline, you can establish performance baselines that prevent your vault from becoming a bottleneck during peak operational hours. If you fail to account for the interplay between high-frequency credential rotation and concurrent session recording, you will inevitably face performance degradation. Your goal is to create a deterministic model that aligns server specifications with the actual behavior of your enterprise environment. This level of precision is the cornerstone of a stable and predictable security architecture. When we shift our focus to the physical and virtual storage layer, we must address the specific requirements of the Vault's storage engine. Calculating IOPS requirements is not merely about disk space. It is about the throughput capabilities of your solid-state drives and their ability to handle concurrent read and write operations. I often see administrators underestimate the metadata growth rates, which can silently consume resources as the vault accumulates thousands of small, granular objects over time. You should treat safe quotas as a hard constraint rather than a loose guideline, as they act as a safeguard against runaway resource consumption within individual safes. Furthermore, your storage layout must be designed with both performance and redundancy in mind, ensuring that the I/O path is not restricted by inadequate bus throughput or improper RAID configurations. Audit retention strategies must be balanced against available storage tiers, choosing appropriate levels for active, hot, and archive data based on the legal and operational requirements of your organization. This is a technical exercise in optimization that ensures the vault remains responsive under varying loads. Network performance and scalability modeling represent the final, often overlooked pillars of our sizing strategy. You must account for intercomponent traffic characteristics, specifically the persistent communication between the vault, the central policy manager, and the privileged session manager. When calculating load balancing requirements, it is vital to assess not just current traffic, but the projected growth over the lifecycle of the deployment. Designing for future organizational growth requires that we build in enough architectural headroom so that horizontal scaling remains a viable option without requiring a total redesign. We document these findings in a technical baseline, which serves as a definitive sign-off document for the implementation design review. This systematic approach allows you to justify specific hardware choices to stakeholders by linking business requirements to measurable resource metrics. By creating these templates, you ensure that your design is repeatable, supportable, and resilient enough for the enterprise environment. Until our next meeting. Hello, and welcome to this deep dive into the foundational requirements for securing our infrastructure. Today, we focus on the essential steps required to harden our servers before we even begin the core product deployment. Hardening is fundamentally an exercise in reducing the attack surface by eliminating unnecessary functionality. When we talk about CyberArk infrastructure, we are dealing with vaults that house the keys to your entire enterprise, which makes their security posture non-negotiable. The primary goal is to strip the operating system down to its absolute essentials, removing any component that could serve as a foothold for an adversary. We approach this by systematically auditing and disabling unnecessary Windows services, as every running service represents a potential entry point or a memory-resident vulnerability. Beyond services, we must unbind unsafe network protocols like SMBV1, which historically has been a significant vector for lateral movement across networks. This process is not just about turning things off. It is about creating a predictable, verified state that aligns with the specific functional requirements of the vault. By employing official hardening scripts provided by CyberArk, we ensure that these modifications follow documented, vendor-tested standards rather than ad hoc configurations. These scripts automate the heavy lifting of registry modifications and security policy settings, ensuring consistency across your deployment. Human error is the most common cause of security misconfigurations, so leveraging automation is the most professional path forward. Once the services are minimized, the attention shifts to the network architecture surrounding our sensitive components. Implementing localized firewall policies is a mandatory progression where we restrict both inbound and outbound communication to the smallest possible set of authorized endpoints. If a component does not explicitly need to talk to a network segment, that communication path should be blocked by default at the host level through host-based firewalls. We further refine this by designing strict network segmentation, ensuring that the vault is not just sitting on a flat, open network where any host can attempt a connection. This often involves the use of jump servers as a single, hardened point of entry, creating a choke point that we can heavily monitor and control. Infrastructure separation is the architectural embodiment of the principle of least privilege, ensuring that management planes are isolated from production data planes. By enforcing these boundaries, we limit the blast radius significantly, even if a perimeter security control is bypassed. Think of this as defense in depth, where we assume the outer layers might fail, leaving the hardened inner core intact and unreachable from unauthorized sources. Secure remote administration is the final piece of this specific hardening puzzle, and it requires careful management of protocols and ciphers. We move away from insecure legacy administration methods, mandating the use of TLS 1.2 or higher for all transit, and explicitly disabling weak cipher suites that are vulnerable to man-in-the-middle attacks. This involves specific registry modifications to force the operating system to prioritize strong encryption standards, effectively rejecting connections that do not meet these criteria. Administrators must be aware that these changes can sometimes break legacy tools or monitoring agents, which is exactly why auditability matters. We must always perform a security validation report after applying these hardened baselines to verify that the system is not only secure, but still compliant with our internal benchmarks. If a system is hardened to the point of being unusable, we have failed the requirement. But if it is functional and insecure, we have failed the mission. Constant benchmarking against a known good state allows us to identify configuration drift, ensuring that the server remains compliant over its operational lifecycle. Maintaining these hardened baselines is an active process, not a static snapshot taken at the time of installation. See you in the next session. Welcome back as we turn our focus toward the operational verification of your Vault networking configurations. In this section, we will establish the rigorous standards required to validate the structural connectivity and security postures essential for a resilient CyberArk environment. Verifying the structural networking configuration is more than just checking that a cable is plugged into a switch or that an interface has an IP address. We must validate the connectivity matrix between all internal components and external endpoints to ensure that the vault can communicate with its satellites, such as the Central Policy Manager and Privileged Session Manager. When we look at the communication requirements, we are specifically checking that the firewall and host-based rules allow traffic on designated ports. A critical example of this is verifying the inbound rule for port 1858, which is the standard port for the CyberArk Vault's internal communication protocol. Without this port being explicitly open and traversable, the vault becomes a silo, unable to pull or push data to the components that rely on it for credential management. We treat these configurations as part of our infrastructure as code, ensuring that the defined state matches the operational reality of the network environment. Analyzing network routing tables and pathing behavior is a defensive necessity when troubleshooting high-latency scenarios between subnets. When traffic moves from a hardened vault to an endpoint or a secondary component, it often traverses multiple routing layers that can introduce overhead or, worse, inconsistent pathing. You should use diagnostic tools to trace these paths, looking specifically for asymmetrical routing where the return packet takes a different path, which can lead to dropped connections in stateful firewall environments. Latency impacts are often subtle, potentially causing timeouts during credential rotation or session initiation that are difficult to correlate back to the network layer. By documenting these expected paths and verifying them against the actual routing tables, you reduce the surface area for mystery connectivity issues. This systematic approach allows us to determine if a communication failure is truly a CyberArk software issue or a symptom of deeper underlying network congestion. Testing connection stability requires us to look beyond simple reachability and simulate conditions where the network might be taxed or unstable. We achieve this by monitoring the connection under load to see how the vault handles degraded performance or intermittent packet drops. Packet inspection is our primary tool here. By capturing traffic, we can observe the health of the connection and identify if packet loss is occurring at the transport or application layer. This is particularly important when evaluating the integration between the vault and external systems, as unexpected latency can trigger failovers in high availability configurations. You must observe these behaviors to understand the resilience of the connection, ensuring that if a degradation event occurs, the system behaves in a predictable manner rather than failing silently. By proactively testing these edge cases, you move from a reactive security posture to one that understands the limits of its own infrastructure. Validating communication security involves a deep dive into the TLS handshakes and the integrity of the encryption layers used across your infrastructure integrations. Every component that connects to the vault must present a valid certificate that chains up to a trusted root, allowing us to perform secure mutual authentication. During verification, you should capture the handshake process to identify potential cipher mismatch issues or expired certificates that might preclude a secure channel from forming. This is where we confirm that the encryption protocols in use meet your organizational security policy standards, such as enforcing TLS 1.2 or higher. Infrastructure integrations rely on these secure channels to maintain confidentiality, and testing them ensures that no man-in-the-middle vector is left open due to misconfiguration. Ensuring these layers are correctly established is the bedrock upon which the entire privileged access management solution relies. Reviewing the post-deployment network topography diagrams is a vital final step to bridge the gap between architectural plans and physical operation. These diagrams should act as a source of truth that reflects your active operational profiles, including firewall rules, VLAN mappings, and component placement. If your diagram shows a direct path that actually routes through an inspection point, you have identified a discrepancy that could cause future support operations to fail. We look for alignment between the intended security zones and the reality of the traffic flows that we validated through our previous testing steps. By maintaining these diagrams and verifying them during every maintenance window, you effectively keep a roadmap of your environment's communication fabric. This preparation is what prevents configuration drift and allows for efficient diagnosis should a service disruption occur later in the lifecycle. I look forward to discussing our next topic with you in the session to follow. Welcome back. In this session, we will examine the deployment and configuration of the Password Vault web access interface, which serves as the primary portal for your privileged users. Deploying the Password Vault web access component requires a disciplined approach to the underlying Microsoft Internet Information Services, or IIS, infrastructure. Before launching the installer, you must ensure that the host server meets all prerequisite roles and features, specifically focusing on ASP.NET, Windows authentication, and ISAPI extensions. If these components are missing or misconfigured, the framework will fail to bind correctly to the web server, leading to cryptic errors during the initial initialization phase. You should always perform a preliminary validation of the server environment to confirm that all mandatory IIS modules are enabled and that the server's permission set aligns with the principle of least privilege. Automating this server preparation through scripts is often advisable to ensure consistency across multiple deployments within your enterprise environment. By treating the server configuration as code, you reduce the margin for human error and guarantee that the dependency map remains stable as you scale your infrastructure. Once the prerequisites are in place, the installation process triggers several critical actions, including the establishment of schema extensions within the digital vault and the creation of the necessary web configuration structures. The application relies on a strictly defined set of XML-based configuration files to communicate with the vault, manage session tokens, and enforce security policies. You will find that the web.config file is where the most sensitive mapping occurs, linking the front-end interface to the secure back-end endpoints. During the installation, the installer will prompt for connection details to the vault. Accuracy here is paramount, as this creates the foundation for your communication chain. After the files are deployed and the application pool is initialized, the system performs a series of background health checks to verify that the PVWA can reach the vault's core services. Any misconfiguration found during this phase will usually manifest as an authentication failure or a service connection timeout in the vault logs. Verification of the initial connectivity requires observing the endpoint responses and ensuring that the basic rendering profiles are correctly served to the client browser. You should navigate to the PVWA landing page immediately following the installation to confirm that the interface loads without significant latency or rendering artifacts. If the page fails to load, the most common culprit is a conflict within the application pool's identity or a misaligned binding in IIS. Often, you will need to inspect the installation logs located in the application directory to trace where the registration of the PVWA user in the vault may have failed. These logs provide a granular view of the interaction between the web server and the digital vault, highlighting whether the issue is related to time synchronization, certificate trust, or incorrect service account credentials. When troubleshooting, prioritize analyzing the framework dependencies and ensuring that the web server's communication port to the vault is not being blocked by local or perimeter firewalls. As your enterprise deployment expands, you will likely need to configure multiple PVWA instances to ensure high availability and load balancing for your users. In this architecture, all instances must be aligned with the same central digital vault endpoints and configured to share the same session management parameters to ensure a seamless user experience. If you decide to deploy in a redundant fashion, you must be meticulous about keeping the configuration files synchronized across all nodes. This involves mapping identical authentication providers and ensuring that the server-side machine keys are consistent, as these are critical for the encryption and decryption of session cookies. When operating multiple instances, think of them as an interconnected ecosystem, where any divergence in configuration can lead to inconsistent session behaviors. Always confirm that each new instance successfully registers with the vault and that the service health monitoring reports are positive for every node in your server farm. See you in the next session. Welcome back. Today, we turn our attention to the critical task of managing high-volume web traffic for your Password Vault web access environment. When we deploy multiple PVWA servers, the primary objective is to maintain high availability and consistent user experience across the infrastructure. A robust application delivery controller acts as the gateway that effectively distributes incoming requests across your pool of PVWA nodes. To ensure this happens seamlessly, we must configure specific mechanisms that govern how the load balancer treats incoming client connections. Without a well-architected load balancing strategy, users may experience intermittent session timeouts or repetitive authentication prompts as their requests bounce between servers that do not share session state. By carefully tuning our distribution algorithms, we minimize latency and ensure that no single server node becomes a bottleneck in your enterprise security architecture. Session persistence, often referred to as sticky sessions, is a fundamental requirement for the PVWA because it ensures that a user's interaction remains tethered to a specific server for the duration of their authenticated session. Since the PVWA relies on session data stored within the server's local memory or temporary caches, breaking this persistence mid-session often forces an immediate logout or an authentication error. You can achieve this using source IP tracking, which bases persistence on the client's network address. But this approach has limitations when many users connect through a single corporate proxy. A more reliable approach involves cookie-based routing, where the load balancer injects a specific cookie into the HTTP exchange. The load balancer then inspects these cookies on subsequent requests to direct the traffic back to the same member of the server pool, maintaining stateful continuity regardless of the client's source network parameters. To ensure the traffic is not directed toward non-responsive nodes, we must implement sophisticated health probes that go beyond simple TCP port checks. A proper health monitor should verify the application layer by targeting specific monitoring URLs that perform a lightweight query against the PVWA to confirm its internal status. If the application returns anything other than a healthy response code, the load balancer must instantly remove that node from the active rotation to prevent end-user disruptions. These probes allow us to define sensitivity thresholds regarding how many failed attempts are required before a node is marked down and how quickly it should be reintegrated once it recovers. Well-tuned health probes provide the necessary safety net that keeps your privileged access management interface reachable even during partial system failures or background service restarts. Integrating SSL/TLS offloading at the load balancer level is a common practice to reduce the computational overhead on the individual PVWA web servers. By centralizing certificate management on the load balancer, you simplify the process of renewing certificates across the fleet, as you only need to update the configuration in one location. However, you must carefully evaluate your internal security policies regarding end-to-end encryption. If your compliance standards mandate that traffic remain encrypted from the client through to the web server, you must configure the load balancer to bridge the traffic rather than terminate it. This ensures that the web server still performs the final decryption, maintaining a chain of trust that satisfies auditors who are concerned about clear text traffic passing through internal network segments or load balancing appliances. When considering traffic distribution algorithms, round robin is the simplest approach, though it often fails to account for the varying load on individual servers. A more efficient alternative is the least connections algorithm, which dynamically assigns new sessions to the node currently handling the fewest active connections. This strategy is particularly effective for the PVWA, where certain actions, like large file imports or batch credential operations, might cause individual server resource utilization to spike. By dynamically observing the current state of the backend, the load balancer makes more intelligent routing decisions that maximize the efficiency of your hardware resources. Always monitor the distribution statistics to identify potential skew, as persistent deviations from an even load distribution may indicate underlying issues with connectivity or configuration discrepancies. Troubleshooting routing discrepancies often involves tracking down issues like session loops or unexpected redirection errors. If you detect that traffic is being routed to servers in a degraded state, examine your probe settings for potential misinterpretation of HTTP response headers. Furthermore, loop detection algorithms on modern load balancers prevent request cycles that can occur due to misconfigured virtual to physical IP mappings or circular routing rules. An uneven distribution of sessions, where one server consistently takes a larger portion of the load, often suggests a failure in how the sticky session mechanism identifies clients behind a NAT or enterprise proxy. Regularly reviewing the logs generated by your application delivery controllers is the most direct way to identify these anomalies and ensure that your traffic management strategy remains aligned with your security and performance requirements. I look forward to seeing you in our next exploration of authentication integration techniques. Welcome back, and today we are shifting our focus toward the security assertion markup language integration within the CyberArk environment. This chapter will equip you with the essential architectural knowledge and configuration techniques required to federate identity management. In modern enterprise architectures, the reliance on disparate identity stores often leads to fragmentation, which is why SAML has become the de facto standard for single sign-on workflows. When integrating CyberArk with an external identity provider, or IEB, we are essentially moving the authentication responsibility away from the local vault or LDAP directory and toward a trusted third-party assertion mechanism. The core of this integration relies on a structured XML exchange between the service provider, which in this case is the Password Vault Web Access, and your chosen IDB. You must understand that the vault itself remains the authorization engine, but the actual verification of the user's identity is delegated. Achieving this requires precise configuration of metadata files, which act as the contract between the two systems. These metadata files contain the public keys and service endpoints necessary to establish a secured, trusted communication channel that ensures the integrity of the authentication assertion. Configuring the integration involves a meticulous dance of certificate mappings and metadata exchanges to ensure that the SOAP or HTTP post bindings are correctly interpreted. When you import the IDP metadata into the PVWA, you are effectively telling the system which certificate should be trusted to sign incoming assertions. If the signature does not align perfectly with the public key stored in the vault's configuration, the authentication will be rejected before the user even sees a login prompt. You must be proactive in managing these certificate lifecycles, as an expired signing certificate on the IDP side will instantaneously break access for the entire organization. Always store these certificates within the CyberArk internal repository rather than relying on disparate local file system paths that might be overlooked during security audits. This centralized approach allows for a cleaner, more maintainable configuration surface that minimizes manual entry errors during critical infrastructure deployments. Beyond mere authentication, the real power of SAML and CyberArk lies in the mapping of claims to local vault entities, such as group memberships and user attributes. The assertion sent by the IBP usually contains specific attribute statements that your CyberArk configuration must parse to determine the user's permissions. This is where you define transformations to ensure that an attribute, like email address or department, accurately maps to existing logical groups within your vault. If there is a mismatch between the attribute values provided by the IBP and the group names defined within the CyberArk platform, the user might authenticate successfully but end up with no access to any safes. You should design these mappings with a focus on least privilege, ensuring that IDP-provided group assignments do not inadvertently grant excessive rights. Consistent attribute formatting is mandatory, as even a simple case sensitivity mismatch can cause systemic failures during the provisioning of user sessions. The workflow can be initiated in two distinct ways, and understanding the nuances of each is required for a seamless end-user experience. Service provider-initiated workflows usually redirect the user to the IEB the moment they attempt to access their PVWA URL, while identity provider-initiated flows rely on the user clicking a tile or link within an enterprise portal. Regardless of the method, the underlying mechanism for token validation remains the same, requiring a successful handshaking of assertions. In cases of authentication failures, you should begin your troubleshooting by examining the SAML tracer, or the logs generated by the PVWA. Look specifically for signature validation errors, time drift discrepancies, or incorrect recipient URLs, which are the most common culprits behind failed requests. Effective auditing requires that you enable verbose logging during the initial phase of deployment to capture the exact payload of the assertion for inspection, which will make identifying discrepancies far more straightforward. Testing these workflows requires a rigorous approach that involves simulating both successful logins and specifically creating scenarios that trigger the fallback mechanisms. If the primary IB is unreachable or the assertion is deemed invalid, the system should fail closed to preserve security. But you might configure distinct behaviors based on your specific risk profile. You must audit these authentication events strictly, ensuring that all redirects are logged with their corresponding session IDs and timestamps. By consistently reviewing the logs for expiration variables within the tokens, you can prevent time-based attacks or replay attempts from succeeding. Establishing this robust integration reduces the administrative burden on your support teams by consolidating user lifecycle management into a single source of truth. As we finalize our understanding of this setup, remember that the goal is a transparent, secure, and reliable authentication path that enhances both security and usability. See you in the next lecture. Welcome back. In this session, we will examine the mechanisms behind directory service authentication mapping to ensure your CyberArk environment integrates seamlessly with your existing identity providers. Integrating an enterprise directory service, such as Microsoft Active Directory or an LDAP-compliant structure, is a foundational step in scaling your privileged access management strategy. By delegating authentication to an external directory, you effectively centralize identity lifecycle management, allowing for granular control of organizational units and security groups directly within the vault. This integration relies on the lightweight directory access protocol to bridge your existing infrastructure with the Vault's proprietary security model. When you map these external structures to CyberArk administrative roles and access permissions, you create a dynamic ecosystem where authorization adjusts automatically as personnel transition across departments. The challenge lies in ensuring that this mapping remains consistent without creating excessive latency or security gaps that could be exploited by unauthorized entities. Achieving this requires a precise configuration of the search bases and the specific filter strings that define which users are authorized to interact with the Vault's administrative interface. Security is paramount when you are extending your directory services, which is why utilizing encrypted communication channels is not merely a recommendation, but an operational requirement. By enforcing the use of certificates over port 636, you establish a secure sockets layer or transport layer security tunnel that shields your binding credentials and directory queries from potential sniffing or man-in-the-middle attacks. You should prioritize the deployment of hardened intermediate certificates to ensure that the Vault trusts the directory controller throughout the entire handshake process. During the configuration phase, you define the routing profiles that determine how requests reach the directory controllers, ensuring that the traffic stays within your trusted network segments. If your directory topology spans multiple geographic locations, you must align these routing parameters with your internal network zones to maintain low latency. Establishing this encrypted framework ensures that your authentication traffic is as secure as the highly sensitive passwords stored within the vault itself. Complexity often emerges when you attempt to synchronize large-scale directory structures, particularly when schema mappings and user provisioning frequencies come into play. Automated provisioning relies on precise attribute mapping, where you designate exactly which directory attributes correspond to CyberArk's user profile fields, such as email addresses or unique identifiers. Synchronization intervals should be tuned to balance the requirement for near real-time updates against the load placed on the domain controllers. Setting these windows too narrow can inadvertently cause performance degradation. Frequent health checks are necessary to proactively identify when the vault loses connectivity with the source directory, which usually manifests as an inability for users to log in or failed authorization assertions. When diagnosing issues, start by verifying your binding credentials, as these are frequently the first point of failure if an account has reached its password expiration date. Monitoring these synchronization blocks allows you to catch inconsistencies in the schema mapping before they lead to mass access disruptions for your end users. Managing resilience in your directory integration requires a robust strategy for handling redundant domain controllers and potential failover events. Within the CyberArk configuration, you should define a failover list that explicitly ranks your directory servers, allowing the system to shift authentication requests to a secondary node if the primary provider becomes unresponsive. By setting appropriate priority parameters, you control the traffic flow and ensure that your most robust controllers manage the majority of the authentication requests. If your directory topology is particularly expansive, consider defining routing path definitions that direct the vault to the closest geographical directory node, which reduces round-trip times during login sessions. Regularly performing audits on these lists is essential because infrastructure changes, such as decommissioning a retired domain controller, can result in the vault attempting to communicate with non-existent services. A well-architected redundancy strategy prevents authentication bottlenecks and ensures that your privileged sessions remain accessible even during local network disruptions. See you in the next session. Welcome back. In this session, we will examine the integration of Remote Authentication Dial-In User Service, or RADIUS, to bolster our PAM ecosystem with robust multi-factor authentication. Integrating a RADIUS server into your CyberArk environment acts as a secondary layer of defense, ensuring that password possession alone is insufficient for gaining access to the vault. When a user initiates a login request through the web interface, The system orchestrates a handshake with the configured Radius server to validate additional identity factors. The integrity of this communication relies heavily on the shared secret, a critical parameter that must match exactly between the CyberArk vault and the Radius endpoint. If these secrets deviate, communication will fail immediately, and the authentication request will be summarily rejected. Furthermore, we must pay close attention to connection timeouts during these exchanges, especially when integrating with hardware tokens or asynchronous push-based authentication systems. Configuring an aggressive timeout threshold can lead to premature request termination, while an overly lenient one might degrade the user experience by delaying the interactive login prompt significantly. When we define the Radius client connection, we are essentially extending the vault's trust to an external network service provider. The mapping of multi-factor challenges requires a deliberate configuration within the web interface settings, ensuring that the expected server response aligns with the expected user input format. In scenarios where the web experience requires a specific prompt, such as a request for a dynamic token code, the Radius protocol must be able to encapsulate these challenges correctly within the access challenge packets. If the implementation is misaligned, the user may face a silent failure where the form does not render the MFA input field, effectively locking them out of the vault. It is useful to think of this as an API contract. The Radius server acts as a service provider, and the vault must strictly adhere to the expected input and output schemas to satisfy the authentication workflow. Maintaining this alignment is imperative for a frictionless user experience during the authentication phase. Troubleshooting the inevitable connectivity drops requires a systematic approach to identifying where the packet negotiation fails. You should begin by utilizing packet tracing on both the vault and the Radius server, as this provides an objective view of the transaction lifecycle. Often, credential rejections are not caused by actual invalid credentials, but by malformed packets or rejected shared secrets that cause the Radius server to drop the request entirely. If you observe authentication attempts that vanish without an error log on the Radius side, the culprit is frequently a network policy or a firewall obstruction that is stripping the UDP packets. Always verify that your network infrastructure permits traffic on the standard UDP ports usually assigned to Radius, as any stateful inspection that drops uninitiated flows will break this mechanism. Establishing a baseline by reviewing successful transaction logs allows you to contrast these with failed attempts when investigating intermittent connectivity issues. Designing for redundancy is an essential aspect of identity architecture, particularly when implementing MFA, as a downed authentication server can lead to a complete operational outage. We accomplish this by designing fallback authentication profiles that allow the platform to fail over to secondary identity providers or designated recovery mechanisms if the primary Radius endpoint becomes unreachable. It is vital that these fallback scenarios are carefully audited to ensure they do not become security bypasses that violate your organizational policy compliance. By tracking verification metrics, such as the latency of MFA processing or the frequency of fallback triggers, you gain observability into the health of your authentication chain. These metrics act as a telemetry layer, alerting administrators if the MFA infrastructure begins to underperform before a total service interruption occurs. Remember that your auditing strategy should capture both the initial Radius request and any associated fallback transitions to provide a complete picture of user access patterns across your privileged endpoints. See you in the next lecture. Welcome back. In this lecture, we are going to explore the integration of public key infrastructure with your CyberArk environment, focusing on how to secure your web access entry points. When we move beyond simple password-based authentication, we often look toward cryptographic evidence to prove identity. In the context of CyberArk, this usually involves leveraging smart card authentication or client-side certificates for password vault web access. The primary goal is to ensure that the authentication process at the web tier is backed by a robust trust model. This requires careful consideration of how you deploy your certificate templates within your environment. If you are using Microsoft Active Directory certificate services, you must ensure that your templates are correctly configured for both client authentication and potentially smart card interactivity. The trust store of the web server must be pre-populated with the root and intermediate certificates of your internal certificate authority to establish a chain of trust. Without a complete chain, the web server will simply reject the handshake during the initial TLS negotiation. leading to authentication errors before a user even sees a login prompt. Once the fundamental trust is established, the next mechanical hurdle is the certificate revocation checking mechanism. A certificate is only as good as its current validity status, which brings us to the necessity of CRLs or OCSP responders. In a secure production environment, you cannot afford to skip this step, as failing to verify revocation status creates a window for compromised certificates to remain active. You must ensure that the web server hosting the private ARC web services can reach the distribution points defined in the CDP extensions of the certificates. If your vault environment sits in a segmented network, you might need to adjust firewall rules to permit egress traffic for these revocation lookups. If the service cannot reach the CRL, you might experience a silent failure where the authentication attempt is dropped, which is often a frustrating issue to debug if you aren't checking your server-side event logs. The actual mapping of these certificates to vault accounts is where the logical link between PKI and access control finally takes shape. We often rely on the user principal name, commonly abbreviated as the UPN, to correlate the certificate identity with a user object in the directory service. When a user presents a smart card, the web access node extracts the UPN from the subject alternative name field of the certificate. This value is then queried against the mapped directory, such as Active Directory or LDAP, to verify the user identity. It is a configuration that requires exact synchronization, as even a minor discrepancy in the attribute mapping will result in an access denial. By enforcing strict certificate constraints, you ensure that only certificates issued by your trusted CAs and containing the expected usage extensions are accepted by your infrastructure. Validation issues are perhaps the most common reason for support requests in this domain. Most of these errors stem from a missing intermediate certificate or an expired revocation list. When auditing these incidents, you should start by examining the web server application logs to confirm the specific failure reason. A common error symptom is a generic 403 forbidden page, which rarely explains that the actual cause was an untrusted CA chain. If you find errors related to certificate validation, verify the entire dependency tree of the certificate presented by the client. You should also ensure that the machine account of the web server has sufficient permissions to query the directory service for the user's attributes. Consistent monitoring of your authentication flows through the internal diagnostic tools will help you identify when these validation checks are failing before they impact a larger user base. Properly securing the session entry point requires rigorous testing of the entire workflow. You should perform end-to-end testing where you simulate a card removal during a session or use an expired certificate to confirm that your revocation policies behave as intended. Access grants should be monitored through the standard Vault auditing reports to ensure that every successful login to the web interface is mapped correctly to the certificate-based session. This visibility is essential for compliance reporting, especially when you are transitioning away from password-only authentication. Remember that your policy definitions must be consistently applied across all web entry nodes in a load-balanced cluster to prevent inconsistent authentication experiences. By treating your PKI integration as a hard security boundary rather than just a convenience feature, you build a significantly more resilient platform. See you in the next lecture. Welcome back, and today we turn our attention to the Central Policy Manager, often referred to as the CPM, which functions as the primary engine for automated password management within a CyberArk implementation. We will navigate the deployment process, focusing on the technical requirements for a successful installation and the subsequent configuration tasks that ensure stability. The deployment of the CPM begins with the execution of the binary installer on a dedicated server, which must strictly adhere to hardware and operating system requirements to maintain consistency. During the initial setup, you are required to define various server parameters that allow the CPM to identify the digital vault and establish a primary communication channel. Because this component interacts directly with sensitive password objects, the security posture of the host machine is paramount, making OS-level hardening steps absolutely mandatory before and after the binary deployment. Hardening involves disabling unnecessary services, closing unused network ports, and applying strict local policies that limit the attack surface of the CPM service itself. You must treat this server as a critical piece of infrastructure, ensuring that no non-essential software resides alongside the CyberArk binaries. Once the software is installed, The next logical step involves configuring the service credentials, which typically utilizes a local structure for managing authentication to the vault. You need to pay close attention to folder permissions, as the CPM agent requires specific access rights to its local storage, including the bin, logs, and temporary directories where password rotation logic is processed. These permissions act as a security barrier, ensuring that the service can interact with its own environment without granting unauthorized access to other local users or processes. Configuring the local any files, particularly those related to the CPM service, dictates how the component interacts with the network and the Vault's internal API. Misconfiguration here often leads to immediate connectivity failures, so verifying the structural paths and Vault address parameters is a task that leaves no room for ambiguity. After the structural connectivity is verified, the installation enters a phase centered on confirming operational cycles, specifically related to the automated mechanisms that rotate passwords. The CPM service performs periodic scans to identify accounts that require management, and these behaviors are controlled by the configuration files within the installation directory. You should analyze the installation logs immediately following the initial start of the service, as these logs contain the raw output of the profile generation processes. If the framework initializes correctly, you will see evidence of the component successfully registering itself with the Vault. Frequent issues at this stage often stem from missing framework dependencies or incorrect registration keys, which must be addressed before the CPM can perform its primary duty of updating credentials. A robust post-installation checklist is your best tool for validation, ensuring that you have not missed any security policies or mandatory hardening parameters during the process. This checklist should include confirming that the CPM service is running under the correct user context and that it possesses the necessary permissions to traverse the file system according to best practices. By using the built-in system verification tools, you can ensure that the link between the CPM engine and the target digital vault is both active and performant. Systematic testing of a single rotation policy provides the final confirmation that the installation was successful and that the heartbeat processes are functioning as expected. Maintaining this methodical approach throughout the lifecycle of the component ensures the environment remains predictable, secure, and fully manageable as you scale your infrastructure. I look forward to discussing how these individual CPM nodes can be scaled across distributed architectures in our next session. Welcome back. In this chapter, we will explore the nuances of designing and implementing distributed multi-CPM architectures to ensure scalability and operational efficiency within your privileged access management environment. When we discuss distributed multi-CPM architectures, we are essentially talking about how to scale the policy engine layer to accommodate the demands of a large-scale enterprise. A single central policy manager is often sufficient for smaller environments, but as the number of managed accounts, platforms, and target systems grows, we encounter performance bottlenecks and physical network constraints. By deploying multiple CPMs, we allow the workload of rotating credentials, verifying passwords, and managing reconciliations to be distributed across different instances. This is not merely about adding servers to a pool. It requires a structured approach to how we delegate responsibilities. We define these responsibilities by creating a clear mapping between specific platforms and specific CPM instances, ensuring that no two managers attempt to act on the same target system simultaneously, which would cause an operations collision. The foundation of managing multiple CPMs lies in the segregation of safe ownership and platform assignment. Every safe in the CyberArk Vault can be configured to be managed by a specific CPM instance by defining the CPM user that has ownership permissions over that safe. When we assign a safe to a particular CPM, we effectively create a logical boundary that prevents other CPMs from polling those accounts for rotation tasks. In an enterprise environment, this allows us to place CPMs geographically closer to the target systems they manage, which minimizes latency and handles bandwidth constraints efficiently. We must ensure that the routing definitions are handled correctly at the network level, as each CPM instance must maintain a persistent, secure connection to the vault while reaching out to target systems across potentially restricted network segments. High availability and load balancing in this context rely on more than just physical redundancy. If a primary CPM fails, we need a strategy to ensure that the workload is resumed by another instance without administrative overhead interfering with critical rotation schedules. This is typically achieved through backup assignment configurations within the platform properties, where a secondary CPM is identified as the failover target. We must manually or programmatically plan these platform migrations so that when one node reports a connectivity issue or a degraded state, the secondary node takes over the responsibility seamlessly. Monitoring these synchronization behaviors involves tracking the heartbeat of each CPM server and analyzing the vault's connectivity profiles to identify potential latency spikes that might precede a failure. To optimize these distributed environments, we should focus on tuning the background task intervals and query distributions. By default, the CPM performs polling operations at intervals that might be suboptimal for high-density environments, leading to unnecessary load on the vault and potential race conditions. Adjusting the delay between polling cycles allows us to smooth out the distribution of processing allocations, ensuring that no single CPM is overwhelmed while others remain idle. We should also analyze the component logs to understand how query distributions are performing under load, as this provides empirical data on where adjustments to the interval settings are required. Maintaining a healthy environment is a continuous exercise in observing how these segregated domains interact with the central vault, ensuring that as the enterprise scales, the policy engine remains a reliable and predictable component of the infrastructure. See you in the next lecture. Welcome back to our exploration of the CyberArk platform architecture. In this lesson, we will focus on the tactical considerations for designing network topologies that effectively support distributed policy management. When we transition from a single-site environment to a complex, segmented enterprise network, our assumptions about connectivity must change. The Central Policy Manager, or CPM, acts as the primary execution engine for credential rotation and management, and its placement dictates the efficacy of the entire security framework. We are essentially mapping execution paths through zones that may possess varying levels of trust and restrictive firewall rules. Designing a robust strategy requires us to define exactly how traffic flows from the CPM to the target systems, often traversing multiple security layers. We must normalize port requirements and ensure that secure lanes are established without creating unnecessary openings in the perimeter. This involves looking closely at how our management traffic, which carries sensitive instructions, is encapsulated and routed across the various segments of the infrastructure. In many modern distributed environments, we encounter the reality of overlapping IP address schemes, particularly after mergers or within multi-tenant frameworks. We cannot simply rely on flat routing tables or assume end-to-end visibility between the CPM and the target devices. Instead, we must architect localization strategies where we deploy additional CPM instances or utilize specific proxy configurations to bridge the gaps between zones. Network Address Translation, or NAT, often enters the picture, requiring careful alignment with the CPM's ability to resolve and communicate with target addresses. If the CPM is placed outside the target segment, we must ensure that the firewall traversal patterns are strictly limited to the necessary ports and that we are not inadvertently expanding the attack surface. By centralizing the management framework while decentralizing the execution point, we maintain a coherent policy set while respecting the granular segmentation of the underlying network. Validation of these designs is a critical step that is frequently overlooked until a management task actually fails. We need to perform an architectural review that specifically tests the viability of the proposed policy deployment paths against the actual security baselines in place. This involves verifying that the communication channels remain within the defined management zones and that there is no unauthorized lateral movement possible from the management components toward production assets. Compliance requirements often mandate that every jump or proxy point in the network is subjected to rigorous auditing. So our design must inherently support the logging and recording of these transit activities. When we align our bridging configurations correctly, we maximize the security boundaries and significantly limit the exposure of our target segments from the central control plane. Strategic planning here essentially means enforcing the principle of least privilege at the network layer, ensuring that the CPM only has the reach it absolutely requires to perform its functions. Think of these design decisions as establishing a set of invariants for your infrastructure. If your network topology is fundamentally porous or poorly defined, no amount of policy hardening within the vault will prevent someone from questioning why management traffic is allowed to traverse segments without inspection. Our objective is to build a topology that is not only functional, but also resilient to the common failure modes of distributed systems. We want to avoid hard-coded dependencies on specific network paths that are fragile and difficult to troubleshoot under pressure. By documenting these paths and validating them against the organizational security baseline, we turn a collection of individual configuration tasks into a cohesive and defensible architecture. This is the difference between simply installing a component and truly integrating it into an enterprise-wide privileged access management strategy. I will see you in the next installment. Welcome back. Let us dive into the intricacies of extending policy enforcement through the advanced configuration of the plugin engine. We will explore how custom script structures and process controllers allow for granular control over privileged credential management. When we discuss the terminal plugin controller, we are essentially looking at the orchestration layer that governs how the central policy manager interacts with disparate target systems. The configuration process files act as the bridge between abstract policy definitions and the concrete low-level actions required to negotiate a shell or a legacy management interface. Within these files, the expectation parameters serve as the primary mechanism for state detection, where the engine evaluates the output of a remote host against anticipated patterns. If the response from the terminal does not align with the defined prompts, the engine defaults to a failure state, which is why precise matching of regular expressions and string literals is vital. Maintaining these configurations requires a disciplined approach to version control, as a single, unmatched prompt can lead to reconciliation locks that persist until manually intervenes. By carefully tuning how the engine identifies these interactive prompts, you effectively reduce the signal-to-noise ratio and the communication stream between the vault and the target asset. This level of configuration is rarely about simple automation and is more accurately described as modeling the behavior of the remote system within the CyberArk ecosystem. Managing password generation involves more than just selecting a length. It is about defining a deterministic policy that satisfies the security requirements of the target system without triggering invalid input errors. You must configure these rules by accounting for specific character patterns, such as mandated special characters or sequences that a particular operating system or application simply refuses to accept. The exclusion matrix becomes particularly important here, as it allows you to filter out characters that might have reserved meanings in command line shells, such as quotes, pipes, or backslashes. If you fail to implement these restrictions correctly, the policy manager will generate credentials that look compliant from a security standpoint, but are functionally unusable, leading to unnecessary account lockouts. Complexity should be balanced against the technical constraints of the platform, meaning your configuration must explicitly map allowed character sets to the technical capabilities of the target endpoint. Always remember that the password generation policy is an expression of the target system's limitations, not merely an arbitrary choice made by the security administrator. Implementing custom error codes is how we translate the raw, often opaque diagnostic output of a remote target into meaningful metrics for the central policy manager. By defining override actions, you can instruct the engine to differentiate between a critical security breach and a transient network hiccup, which is vital for effective retry logic. The timeout boundaries must be calculated based on the latency of the network path and the typical processing time of the target application to prevent premature termination of management actions. If you set these thresholds too aggressively, you invite false negatives where the plugin terminates prematurely while the task is still validly processing in the background. Conversely, excessively loose boundaries can result in unmanaged resource leakage, where the engine holds an open connection far longer than necessary. Effective error handling is therefore an exercise in mapping specific failure patterns to predictable recovery behaviors that maintain the integrity of the managed account's lifecycle. Optimizing the performance of the plugin engine requires a careful balance between thread usage and memory allocation on the server hosting the policy manager. Each active plugin instance consumes system resources, and when managing thousands of accounts, the cumulative effect can lead to thread exhaustion if the execution speeds are not tightly regulated. Tracking the consumption patterns of your custom scripts allows you to identify bottlenecks where the engine lingers on tasks that could be parallelized or optimized through more surgical logic. If you encounter plugin format errors, the first point of investigation should always be the parsing of the script execution blocks, which are sensitive to unexpected whitespace or encoding inconsistencies. Adjusting these blocks to be more robust ensures that the plugin can handle variations in the target's output without crashing the entire orchestration task. Proper optimization is a continuous feedback loop where you measure the resource footprint of your plugins and adjust the configuration parameters to align with the overall health of the environment. See you in the next lecture. Hello, and welcome back to our deep dive into the practical administration of a CyberArk environment. Today, we are focusing specifically on the automated mechanisms used to map out your infrastructure and identify privileged accounts you might not even know exist. In any reasonably sized enterprise, the sprawl of privileged credentials is a reality that often outpaces manual management. When we talk about automated account discovery, we are essentially talking about the process of instructing the CyberArk discovery engine to traverse your network boundaries and directory structures to look for unmanaged entities. To configure this effectively, you must define specific discovery scopes that determine exactly where the scan should look. By setting granular network boundaries such as IP ranges or specific subnets, you prevent the engine from scanning segments of the network that are irrelevant or outside your security purview. Furthermore, you must define the target directory structures if you are querying LDAP or Active Directory, ensuring that the engine has the appropriate permissions to read those objects without triggering security alerts for recursive crawling. The scheduling interval is equally important, as running these scans during peak business hours can saturate the network or impact system performance on the targets you are attempting to audit. Once the discovery engine identifies potential targets, the next step involves implementing rule-based categorization to make the data actionable. Without a clear set of rules, you will be left with a haystack of accounts where you cannot distinguish between a highly privileged service account and a local guest user. By defining onboarding parameters, you tell the system that any discovered account matching a specific pattern, such as an account starting with a particular prefix or possessing administrative group membership, should be treated with a higher priority. These rules allow for automatic safe assignment, which is a critical piece of the workflow that ensures discovered credentials are moved immediately into a protected vault rather than remaining vulnerable on the target host. By utilizing standardized templates for these onboarding tasks, you ensure that as soon as a machine or account is found, it inherits the platform configurations, rotation policies, and security controls that you have already established for the rest of your fleet. Effective administration requires that you do not simply set these automated processes and walk away, as discovery engines are prone to occasional failures or data gaps. You must regularly analyze the discovery engine logs, specifically looking for credential failures or target mismatches that indicate a misconfiguration in your scan credentials. If you see recurring errors, it often points to a mismatch between the permissions granted to the discovery scan user and the security requirements of the target system, such as a missing privilege to enumerate local group memberships. Analyzing access drops is vital to understanding whether network security devices like firewalls or intrusion detection systems are flagging the discovery traffic as suspicious activity. By keeping a close eye on these logs, you ensure that your asset inventory remains as accurate as possible, preventing compliance drift where some servers are managed while others remain invisible and unprotected. Finally, we need to discuss the optimization of scan performance so that our security efforts do not disrupt the operational availability of the business. Scanning is inherently resource-intensive, so you should tune your discovery jobs by staggering the intervals and limiting concurrent connections to sensitive hosts. You can often minimize the impact on host system resources by offloading the scanning workload or by throttling the discovery service during heavy enterprise usage times. Once the discovery processes are optimized, the value is found in the inventory reports that allow you to conduct a meaningful security gap analysis. Reviewing this dashboard against your known asset database helps you pinpoint which segments of your infrastructure lack the security controls you require, providing you with a roadmap for further hardening and credential rotation deployment. By maintaining an accurate view of your privileged landscape, you turn the daunting task of enterprise security into a manageable, data-driven methodology that keeps your posture defensible against internal and external threats. I will see you in the next lecture. Welcome back. In this session, we will examine the mechanics of enforcing credential rotation policies within the CyberArk environment. Credential rotation is the backbone of a robust, privileged access management strategy because it minimizes the window of opportunity for an attacker to leverage compromised credentials. Within the CyberArk platform, we manage this through the Central Policy Manager, or CPM, which dictates the frequency and manner in which passwords are updated on target systems. When you configure your master policies, you are essentially setting the guardrails for how the CPM interacts with these platforms. Tuning these rotation frequencies is not merely a task of setting the number of days between password changes, but is a careful balancing act of security requirements versus operational stability. You must ensure that the platforms defined in your environment are sufficiently capable of handling frequent password updates without causing disruptions to automated service accounts or critical application workflows. If you force a rotation cycle that is too aggressive for legacy hardware or sensitive middleware, you risk triggering service outages that can take hours to remediate manually. The precision of your rotation configuration often relies on the ability to trigger these actions immediately when specific conditions are met. CyberArk platforms allow for immediate rotation triggers that can be engaged when an account is onboarded or when a verification check fails. These verification checks are critical because they act as a heartbeat mechanism, confirming that the credential known by the vault is indeed the same credential currently in use on the target system. When these two values do not match, the synchronization window collapses, and the CPM must intervene to reconcile the discrepancy. You need to configure these windows with enough latency to account for replication delays in distributed environments while remaining tight enough to maintain security integrity. If the synchronization window is too wide, you leave an unnecessary gap where stale credentials persist, which could be exploited while the system waits to verify its state. Managing automatic reconciliation configurations requires a deep understanding of administrative account elevation rules on your target systems. Reconciliation is a fail-safe mechanism where the CPM uses a privileged account with higher permissions to reset the password of a managed account that has become out of sync. To implement this, you must link the managed account to a sufficiently privileged reconciliation account and ensure that the often restricted administrative user has the rights to perform the password change operation. Elevation rules frequently come into play here, especially on modern operating systems that require specific authentication sequences or privilege changes to modify sensitive security objects. Always perform a thorough review of the end-to-end process, confirming that the elevation sequence succeeds before relying on it for automated disaster recovery of a credential. If the administrative account lacks the necessary rights, or if the elevation rule is improperly formatted, the reconciliation attempt will fail, leaving the system in a locked state until manual intervention occurs. Reviewing the application cycles of your system policies is a process that requires consistent attention to the rollout across your safes. When you modify a policy parameter, it is not always immediately applied to every object stored within a safe due to internal caching and background processing tasks. You must verify that the policy application cycles have synchronized across the vault, ensuring that the new rotation settings are being respected by all CPM instances assigned to those safes. This is particularly relevant in high-scale environments where multiple CPMs operate on different subsets of accounts to optimize throughput and management load. If you discover that specific accounts are failing to rotate according to the new policy, you are likely looking at a propagation delay or a platform override that is taking precedence over the global master policy. Troubleshooting these rotation policies requires a methodical approach, specifically checking for platform overrides or enforcement blocks. Often, an issue arises not from the policy itself, but from a local platform configuration parameter that has been set to disable the rotation capability for a sensitive subset of systems. You should verify if any change password in vault or immediate interval parameters have been manually modified, or if the allow manual change setting is blocking the automated process. When examining logs, focus on the platform logs generated by the CPM, as these contain granular evidence of failed handshakes or policy enforcement denials. If the target system reports an error during the change request, be sure to confirm that the platform connectivity settings, such as port configurations and supported protocols, remain consistent with the current security standards in your network. Finally, documenting your configurations is the only way to demonstrate effective compliance and maintain a reliable internal audit profile. You should treat your platform configuration files as architectural documentation that tracks why certain intervals or reconciliation rules were chosen for specific user populations. During an audit, you will be expected to produce evidence that rotation is active, regularly validated, and failing over to reconciliation as designed. By standardizing the format of these profile updates, You create a repeatable verification process that removes ambiguity during high-pressure security reviews. This documentation serves as the ultimate source of truth for both your operations team and your organization's security auditors. See you in the next lecture. Welcome back to our exploration of the CyberArk PAM solution, where today we shift our focus toward the architectural deployment of the Privileged Session Manager. In this chapter, we will master the installation, hardening, and operational integrity of the PSM component within your Privileged Access Management ecosystem. Deploying the Privileged Session Manager begins with the binary installation process, which transforms a standard Windows server into a dedicated gateway for proxied administrative sessions. Before you initiate the setup, you must ensure the underlying server meets all prerequisites, most notably the installation of the remote desktop session host role. Without this role, the server cannot host concurrent sessions, which is the foundational requirement for the protocol isolation that the PSM provides. During the installation process, you are essentially establishing a hardened conduit that acts as a jump server, shielding your target endpoints from direct network access. Proper server adjustments are critical here, as the PSM relies on a precise configuration of the local environment to manage the lifecycle of ephemeral RDP, SSH, and database sessions. You must pay close attention to the terminal services licensing configurations, as the PSM operates as a multi-session environment that effectively acts as a terminal server for your privileged users. If these terminal server parameters are not perfectly aligned with your environment scale, you will encounter session latency or, worse, blocked connection attempts that hinder your administrative workflows. Once the binary installation and role configurations are settled, the focus shifts to internal resource management, specifically the storage structures required for session auditing and recording. You must define dedicated, high-performance storage paths for session recordings, ensuring that the local service account has sufficient permissions to write into these protected directories. A common operational failure occurs when permissions layouts are misconfigured, preventing the PSM from committing the captured session streams to the vault or local storage. You should implement a rigid folder structure that separates recorded video fragments from temporary metadata, as this simplifies the eventual cleanup and archiving processes enforced by your retention policies. The initialization phase is where the rubber meets the road, as the PSM component must perform an authenticated handshake with the vault to retrieve its unique credentials and operational configuration. If the connectivity check fails during this initialization, you must verify the vault's host address, the port availability through any intervening firewalls, and the validity of the component's authentication certificate. Hardening is not merely a suggestion in the context of a privileged gateway. It is a mandatory operational requirement that mitigates the risk of a compromised PSM becoming an entry vector for lateral movement. Following the initial software deployment, you must apply specific group policy templates that disable unnecessary services, restrict local interactivity for non-authorized users, and enforce a clean registry profile. These policies ensure that the server environment remains static, preventing software drift that could weaken the security posture of the session recording engine. Beyond GPOs, you must scrutinize the registry modifications that dictate how the PSM handles clipboard redirection, drive mapping, and printer integration, as these are common attack surfaces. By applying these profiles consistently, you reduce the attack surface to the bare minimum required for the PSM to function as a session proxy. Failure to harden the server effectively negates the security benefits of the session isolation, leaving your infrastructure open to the very risks you are deploying the PSM to prevent. Troubleshooting the PSM requires a methodical approach to analyzing initialization logs and tracing component startup behaviors. When a session fails to launch, the first point of analysis should always be the logs generated during the initialization sequence, which reveal whether the component successfully established a trusted relationship with the vault. Many failure modes are rooted in configuration mismatches within the connection components, often stemming from incorrect parameter definitions or missing dependencies for specific target applications. You should look for indications of authentication failures, timeout errors, or connectivity blocks that might suggest an issue with the underlying network route or a certificate handshake error. By systematically validating these logs, you gain visibility into whether the problem lies within the session manager itself or in the communication pipeline between the gateway and its target server. Mastering these logs ensures that you can rapidly diagnose why a session might be failing to record or why a user might be getting dropped mid-session, maintaining the required operational uptime for privileged access. See you in the next lecture. Welcome back to our exploration of the PSM for remote access infrastructure. In this lesson, we will focus on deploying the HTML5 gateway, which enables clientless session connections directly through a web browser. The HTML5 gateway acts as an intermediary, translating web-based protocols into the RDP or SSH streams required by target systems. Under the hood, this component heavily leverages Apache Guacamole-based architecture to facilitate browser-based connectivity. When a user requests a session through the privileged session manager, the gateway establishes a secure bridge without necessitating local client software installation on the endpoint. You must consider the placement of this gateway within your network topology, typically positioning it behind a secure web proxy to obfuscate the backend infrastructure details. Properly configuring certificates is paramount here, as the gateway must terminate TLS connections from the user's browser while simultaneously managing outbound secure tunnels. Neglecting the certificate chain validation often results in rejected sessions or security warnings that frustrate end users during their routine workflows. To establish a functioning pathway, you need to map connection routing paths from the web interface directly to your session managers. This isn't just about pointing IP addresses at one another. It implies a deeper configuration of the gateway's connection metadata. You must ensure that the privileged session manager instance recognizes the HTML5 gateway as a trusted entity by explicitly defining it in the PSM configuration files. If these paths are misconfigured, the connection handshake will fail at the web interface level, often leaving the user with a blank screen or a dropped connection notification. Always verify that your network firewalls allow traffic between the web access interface and the gateway on the designated management ports. Ensuring these pathways are defined with logical consistency allows the system to route traffic efficiently, regardless of which session manager currently holds the active connection. Security relies heavily on enforced TLS settings across all segments of the session pathway. You have to configure the gateway to mandate strict TLS enforcement, rejecting any attempts at insecure cleartext communication. This involves deploying trusted certificates that align with your organizational public key infrastructure to validate the identity of the gateway nodes. If the client browser does not trust the gateway certificate explicitly, the session will be blocked before it even attempts to negotiate the backend protocol. When dealing with troubleshooting scenarios, focus on the rendering issues that frequently arise from incompatible browser versions or blocked WebSocket traffic. Connection drops are often symptomatic of certificate mismatch errors or inter-node communication timeouts that occur during the initial protocol negotiation sequence. Keyboard mapping faults represent another common category of issues you might encounter in a production environment. These usually occur because the local browser character encoding does not map correctly to the target server's keyboard layout settings. To mitigate this, investigate the guacamole properties and ensure that the keyboard mapping parameters are configured to match the localized environments of your target endpoints. When your deployment scales to meet higher concurrent demand, you should transition to a multi-instance model with load balancing. These stateless configurations allow you to distribute the inbound traffic across a cluster of HTML5 gateway instances, preventing any single point of failure. By monitoring throughput metrics and session latency, you can effectively plan your scale-out strategy to maintain performance during peak access hours across your entire enterprise architecture. I will see you in the next lecture. Welcome back. In this chapter, we will explore the engineering of custom connection components to launch specialized client applications through secure proxy frameworks. When the out-of-the-box connection components do not meet the specific requirements of a target application, you must design a custom solution to bridge the gap. This involves deep configuration of target application parameters, specifically defining how the client software is invoked and identifying the necessary command line arguments. You need to map these variables within the platform definitions to ensure the privileged session manager correctly orchestrates the execution pathway. A critical aspect here is handling window titles and auto-it script definitions, which act as the mechanical hands of your automation. By precisely defining these triggers, you ensure that the session proxy can reliably interact with the login fields of the target application. This orchestration requires a clear understanding of the application's unique layout, as the proxy must identify where to inject credentials without human intervention. Without this precise mapping, the session gateway will fail to perform the automated authentication step upon application launch. Managing shadow user profile attributes is a core component of maintaining secure and isolated execution environments for these sessions. You must consider how localized resource isolation variables affect the behavior of the target software, particularly regarding permissions and user context. When a session is initiated, the privileged session manager creates a unique environment that must prevent the application from bleeding information or access into the broader system. Configuring these attributes correctly ensures that the session remains contained while still providing the necessary access for the user to perform their operational tasks. You should pay close attention to how the operating system handles the identity of the user running the application on the proxy server. This involves configuring the component to work within the confines of the Windows profile, ensuring that temporary files, registry entries, and cache credentials are cleaned up appropriately after the session concludes. Failure to properly isolate these resources can lead to security vulnerabilities or data leakage between consecutive sessions. Troubleshooting the automation of these custom components often shifts focus to the mechanics of the client application itself, such as managing crashes or handling unexpected window detection failures. A common issue arises when the target application takes too long to load, exceeding the defined timeout period, or when a pop-up window shifts the focus away from the main login element. To mitigate this, your AutoIt script should include robust logical checks that verify the presence of specific window components before attempting to inject metadata or credentials. When an automation block occurs, it is rarely a failure of the vault itself, but rather a misalignment between the script's expectations and the actual state of the application's graphic user interface. You must carefully monitor the execution logs to identify the exact point where the interaction fails, often by auditing the window handle acquisition or the success of the simulated keystrokes. Maintaining a consistent recording of these interactions is equally important, as it provides the forensic trail necessary to verify that metadata injection occurred exactly as intended. Testing these custom connections requires a methodical approach to confirm both the functionality of the session launch and the integrity of the session recording. As you prepare these components, ensure that you are validating the operational flow from end to end, confirming that the user is placed into the target environment with the correct permissions. During the validation phase, you should focus on the metadata injection process, ensuring that the sensitive credentials never touch the disk in plain text, but are passed securely from the vault session to the target interface. Continuity of the recording is also a vital metric, as any disruption in the connection component's logic can lead to fragmented session logs or incomplete audit trails. If everything is configured correctly, the privileged session manager will act as a transparent intermediary, allowing the user to experience a seamless login while the underlying infrastructure maintains full oversight and security compliance. Verifying these connections under various load conditions ensures that your design remains stable and performant in a production environment. I will see you in the next lecture. Welcome back. In this lecture, we will explore the intricacies of the universal connector architecture and how it extends our session management capabilities to third-party software. The universal connector acts as a bridge between the privileged session manager and applications that do not have native integration within the CyberArk ecosystem. At its core, this architecture relies on a wrapper framework that intercepts the launch process of an application to facilitate credential injection. When a user initiates a session, the PSM service invokes the connector, which in turn acts as a mediator by programmatically passing credentials into the target application's login fields. To ensure security, these parameters are communicated securely through the shadow user session, preventing clear text exposure within the environment. This mechanism effectively turns any local or terminal-based application into a managed resource, allowing us to enforce consistent security policies across diverse platforms. Properly architecting these connectors requires an understanding of how the wrapper communicates with GUI elements or terminal streams to ensure seamless session establishment. Deploying these connectors successfully involves packaging client installers and managing dependencies across our session manager farms. Each target application might require specific runtime libraries or client-side software, which must be installed consistently across all PSM nodes to ensure high availability and load balancing. Configuration management here is paramount, as any discrepancy in the installation path or dependency version will lead to delivery issues and failed connections. We must treat these components as code, ensuring that we document the architecture, specific operational requirements, and deployment checklist to prevent environment drift. By standardizing the distribution of these components, we ensure that every session manager in our farm provides a uniform experience regardless of which node handles the request. Auditing and compliance remain significant drivers for session management, and the Universal Connector supports this through detailed configuration of recording options. We can enable keystroke logging and window title tracking to capture the context of every administrator action during a session. These auditing parameters are mapped to the connector configuration, ensuring that the PSM captures the necessary metadata for forensic analysis. If we encounter issues, such as a mismatch between the connector expected parameters and the actual window state, the log files within the PSM become the primary source of truth. Troubleshooting usually involves inspecting these logs for execution discrepancies, verifying that the wrapper is correctly identifying the target fields, and adjusting the timeout variables to accommodate application latency. Consistent maintenance and periodic verification of these configurations are essential to maintain the integrity of our privileged audit trails. See you in the next lecture. Welcome back. Let us focus our attention on the specific requirements for deploying a privileged session manager for SSH within a Linux infrastructure. Installing the privileged session manager for SSH, commonly known as PSMP, onto a Linux server requires a disciplined approach to system preparation and configuration. Before executing the installation scripts, you must ensure the underlying operating system is properly hardened by removing unnecessary packages and services that could present an increased attack surface. A clean installation relies on satisfying specific dependencies, such as the correct versions of OpenSSH and other common libraries that the proxy daemon requires to function efficiently. You will typically interact with the installation script provided in the distribution package, which handles the creation of necessary file system structures, user groups, and permissions. It is critical to monitor the output of these scripts, as they configure the core proxy daemon parameters and initialize the connection to the digital vault. Always verify that the service accounts created during the installation maintain the principle of least privilege, as these accounts will interface directly with your hardened Linux environment. Once the core files and services are in place, the integration with the vault must be validated through the secure administrative pipeline. This process involves the registration of the PSMP server as a component within the CyberArk environment, which relies on the successful generation and exchange of authentication credentials between the proxy and the vault. You should verify that the proxy can establish a reliable connection to the vault services, as network binding issues or firewall restrictions often cause silent failures that manifest only during the actual connection request. Configure your local Linux firewalls to permit traffic strictly on the ports required for vault communication and the intended SSH proxy traffic. If you encounter errors, inspect the specific log paths generated by the installation process, as they usually provide clear indications of authentication mismatches or connectivity drops. Remember that the proxy daemon behaves as a transparent intermediary, so its ability to communicate with the vault is the single most important factor in the success of the installation. After the initial installation and vault registration, you must test the actual session routing and terminal command capture mechanisms to ensure they meet your security requirements. The PSMP performs a critical role in intercepting the user's connection request, authenticating it against the vault, and then establishing a secure SSH tunnel to the target system. You should conduct a series of connection tests using different access patterns to ensure that logging profiles are active and that all session activities are being recorded as expected. If the proxy fails to route the traffic, investigate the configuration files for misaligned target parameters or incorrect routing rules that might prevent the daemon from identifying the intended destination. Often, permission errors on the storage volumes designated for session recordings can disrupt the logging process, so verifying the directory ownership and right permissions is an essential troubleshooting step. By methodically checking these parameters, you ensure the proxy remains a robust safeguard that provides both visibility and control over privileged SSH access within your infrastructure. See you in the next lecture. Welcome back. We are moving into the intricacies of configuring SSH proxy policies to secure privileged access across your infrastructure. This lecture focuses on the granular enforcement rules and session management parameters required to govern secure shell traffic through the CyberArk PSM. Configuring connection policies for SSH proxies requires a methodical approach to balancing strict security constraints with the operational needs of your privileged users. When we define these policies, we start by establishing the core connection parameters that dictate how the PSM mediates the traffic between the client and the target server. Within the platform management interface, you must configure the SSH proxy settings to define whether the connection is intercepted or transparently proxied, as this fundamental choice dictates the auditing capabilities available. You will find that defining these policies allows for the implementation of command authorization, which acts as a gatekeeper for sensitive administrative actions. By establishing a clear separation between authorized and unauthorized commands, you effectively reduce the blast radius should a credential be compromised or a user session be subverted. This mechanism is not merely an optional feature, but a core governance requirement in any mature privileged access management program. You should approach these settings by first identifying the typical command sets required for specific administrative roles, ensuring that your policies provide enough flexibility for legitimate work while maintaining a posture of least privilege. Remember that every connection policy should be validated against the actual target device requirements to ensure that proxy side modifications, such as environment variable injection or header manipulation, do not break the underlying protocol negotiation during the initial handshake. Once the basic connection is established, the enforcement of command restrictions becomes the primary defensive layer. Implementing blacklisting or whitelisting necessitates a solid understanding of regex matching syntax to ensure that your filters are both effective and performant. You might, for example, wish to block destructive commands like rm or mkfs while allowing standard diagnostics tools, and regex enables this granular control without requiring a comprehensive list of every potential shell command. When designing these regex patterns, be mindful that overly permissive expressions can lead to security gaps, while overly restrictive ones can trigger false positives that halt legitimate administrative workflows. It is also important to consider the action profiles assigned to these rules, which determine whether an unauthorized command simply fails, triggers an alert, or results in immediate termination of the entire session. By fine-tuning these inspection actions, you align the automated response with your organization's risk appetite, ensuring that critical infrastructure remains protected without causing excessive operational friction. Always perform thorough testing of your regex logic in a sandbox environment before promoting it to production, as an incorrectly structured pattern could inadvertently block all traffic or fail to capture the intended security violations. Beyond command control, the session recording parameters serve as the definitive audit trail for all activities occurring within the proxied SSH tunnel. You must define keystroke capturing and terminal logging settings to ensure that every character input and output is captured and sent to the vault storage area. Careful consideration must be given to storage allocations and remote locations, as high-frequency session recording can consume significant disk space and I/O resources on your vault servers. I recommend organizing your storage architecture to account for retention policies, ensuring that logs are rotated or archived before they impact the performance of the live platform infrastructure. Furthermore, you can supplement these logs by integrating custom syntax shortcuts that provide a more intuitive interface for users when establishing connections to complex, multi-hop targets. These shortcuts, along with managed bypass variables, allow you to streamline the user experience while still enforcing the mandatory proxy path, thereby maintaining visibility and control even for the most complex access requirements. By standardizing these recording and navigation settings, you create a predictable environment where security administrators can easily retrieve logs during an incident investigation or regular compliance audit. SSH key authentication management represents the final piece of the architecture, where you define how the proxy validates the identity of the user and the target. Managing key parameters involves configuring whether the PSM performs authentication handoffs or maintains separate sessions, which directly influences the trust boundary between the components. In some environments, implementing bypass workflows may be necessary for specific, low-risk administrative tasks, but these deviations must be explicitly configured and tightly monitored to prevent unauthorized credential exposure. Target verification configurations add an extra layer of assurance, checking the host keys of destination systems to prevent man-in-the-middle attacks at the proxy level. If you encounter issues such as proxy drops or unexpected session terminations, the first place to look is the configuration file integrity. as syntax corruption can lead to silent failures that are difficult to diagnose. By monitoring the relevant system logs and validating your configuration entries against the expected schema, you can resolve these issues efficiently before they manifest as service outages for your privileged users. Dealing with these nuances requires a disciplined focus on alignment between the client-side configuration, the proxy enforcement rules, and the target system security requirements. See you in the next lecture. Welcome back. We are now looking at the operational procedures surrounding data protection and the CyberArk replication utility. In this chapter, we will master the technical implementation of data protection strategies using the CyberArk replicate utility to ensure organizational continuity. You will learn to automate backup workflows, manage secure storage targets, and execute rigorous integrity verification procedures, essentially hardening your deployment against catastrophic data loss. When we approach backup strategies within a CyberArk environment, our primary goal is the reliable replication of the digital vault. The replicate utility functions as the backbone of this operation, allowing us to transmit vault data to a secondary or disaster recovery site. To begin, we must carefully configure the initialization parameters within the replication configuration files. This includes defining the source and target vault addresses alongside the timing intervals that dictate when synchronization occurs. We categorize these tasks into full or differential downloads, where a full backup captures the entire encrypted metadata and object store, while differential tasks focus only on incremental changes. Establishing a predictable schedule for these tasks is essential to avoid competing for network bandwidth during peak production hours. Automation, in this context, is not merely a convenience, but a mandatory requirement for maintaining a consistent state across replicated infrastructure. Securing the storage targets where these backups reside requires a rigorous application of the principle of least privilege. We must ensure that the backup destination only accepts traffic from authenticated and authorized vault servers, typically restricted via hardened network access lists. Beyond simple network visibility, the data residing on these targets must be encrypted at rest, utilizing robust key management routines to safeguard the encryption keys themselves. If an attacker gains access to the backup files but lacks the cryptographic keys managed through your key management system, the data remains unreadable. Furthermore, it is not enough to simply store data. We must also implement automated verification routines. This involves regular integrity checks of the backup sets to confirm that no bit rot or corruption has occurred during the transfer or long-term storage phase of the lifecycle. A backup strategy that has never been tested is effectively a strategy that does not exist. We maintain business continuity by periodically executing test restorations in an isolated or alternative safe environment. This process validates that the backup files are not only present, but functionally decryptable and mountable by a disaster recovery instance of the vault. During these tests, we observe the time taken for the restoration process, ensuring it aligns with our defined recovery time objectives and business continuity timelines. Should a restoration take significantly longer than expected, we must evaluate our storage throughput and data compression settings. These restoration drills expose potential configuration gaps that might otherwise remain hidden until an actual production outage occurs, at which point remedial action is far more costly. The operational reality of a replication infrastructure is that anomalies will eventually occur, making log analysis a core component of daily maintenance. We monitor the replication log files to identify transmission drops or synchronization failures that might occur due to intermittent network latency. By tracking these metrics, we can often identify data bottlenecks that degrade the performance of the Vault synchronization engine during high traffic periods. If logs indicate an increase in failure rates, we verify the connectivity status, the status of the Vault services, and the credentials used by the replication user. Consistent tracking of these logs allows us to transition from a reactive posture toward a proactive one, where we address potential failures before they compromise the consistency of our disaster recovery site. Every administrator must be intimately familiar with the interpretation of these log patterns to maintain a healthy and resilient CyberArk ecosystem. See you in the next lecture. Welcome back to our exploration of the CyberArk infrastructure lifecycle. In this session, we investigate the systematic process of applying functional patches to distributed components to ensure long-term stability and security. Maintaining a complex, privileged access management environment requires more than initial configuration. It demands a disciplined approach to component patch management. When CyberArk releases a security update or a functional patch, you cannot simply apply it across your entire infrastructure without a rigorous preparation phase. The first step involves a careful review of release notes to identify exactly what the patch addresses, whether it is a vulnerability remediation or a feature-driven improvement. You must assess the risk profile of each component, particularly regarding dependency matching between the digital vault, credential providers, and the web-based interfaces. It is rarely the case that you can upgrade one component in isolation, so verify that your version matrix aligns with the expected compatibility requirements of the new patch. Always perform your initial testing in a non-production environment that mirrors your live configuration as closely as possible, as this allows you to observe how the new binaries interact with your existing policies and custom plugin engines. Once you move from testing to execution, your strategy should focus on minimizing service disruption through a rolling patch installation. Instead of taking the entire infrastructure offline, you can systematically patch web interfaces or session managers in a staggered sequence to ensure high availability is maintained throughout the process. This controlled deployment style relies on a well-defined sequence where traffic is redirected or drained before a component is updated and returned to the cluster. During these installations, you must monitor the service logs and resource utilization metrics to ensure the software initializes as expected in its new state. If you are managing a distributed architecture with multiple policy engines, prioritize the updates to ensure that the core management services remain operational. The goal here is to maintain a predictable, repeatable process that avoids the fragility often associated with ad hoc updates in distributed systems. Post-patch validation is a critical phase that involves more than just checking if the service process is running. You must execute your enterprise verification suites to confirm that core PAM functionalities, such as account discovery or privileged session initiation, remain intact. If your environment relies on specific authentication mappings, verify these flows to ensure the patch has not introduced unexpected behavior in your directory service integrations. Continuous monitoring during this phase is essential, as subtle issues like increased latency or configuration drift can manifest only under load. Because you are handling sensitive privileged sessions, ensure that session recording and monitoring components are functioning at the expected capacity before considering the maintenance task finished. A patch is not successfully deployed until the entire ecosystem regains its state of functional equilibrium across all geographical nodes. Perhaps the most important aspect of any maintenance plan is the preparation of a robust rollback procedure. Designing a mitigation strategy implies that you have a set of clear triggers that indicate when an upgrade has failed, such as a persistent service crash or a critical version incompatibility in the database schema. You should always maintain a backup of your configuration files and, where applicable, system snapshots that allow you to revert to the pre-patch state within a defined recovery time objective. Without a pre-tested rollback mechanism, you risk turning a manageable software update into a catastrophic service outage. Documenting the specific patch levels and configuration changes in a centralized compliance matrix is the final step in ensuring long-term accountability. This record-keeping allows you to track exactly which components are running which versions, simplifying audit requirements and planning for future infrastructure upgrades. See you in the next session. Welcome back, and let's examine the technical requirements for maintaining component currency within a CyberArk environment. Upgrading your privileged access management environment is rarely a simple task of running an installer, as it requires a disciplined approach to ensure that the entire ecosystem remains operational. You must begin by consulting the official compatibility matrix provided by CyberArk, as this document dictates the specific order of operations and identifies which version pairings are technically supported. A common pitfall involves attempting to upgrade downstream components before the vault has been successfully transitioned to the target schema version. The digital vault serves as the foundation for the entire architecture, and its database schema modifications are usually non-reversible, which is why testing these steps in a staging environment is mandatory. You need to verify that all hardware and operating system prerequisites are met before initiating any service upgrades on the server nodes. It is essential to account for the dependencies between the vault, the privileged session manager, the central policy manager, and the password vault web access. By formalizing your upgrade path, you reduce the risk of service disruption and ensure that security policies remain enforced throughout the transition period. The upgrade process inherently starts at the center of the architecture with the digital vault, where you must first ensure that your backups and disaster recovery sites are synchronized and verified. Once the vault platform upgrade is initiated, the database upgrade and schema conversion process begins, which often involves running specific utilities to ensure data integrity. After the vault services are restored and validated, you turn your attention to the dependent components, applying updates in a sequential and logical fashion. For example, if you are managing a cluster of components, such as a farm of web access servers or session managers, you should adopt a staggered upgrade approach. This strategy involves upgrading one node at a time while monitoring load balancer health signals to ensure that high availability remains intact. Post-upgrade validation is the final critical step, where you confirm that integrated authentication, policy execution, and recording services behave as expected against the newly committed database schema. You should prioritize the resolution of any configuration file conflicts, specifically looking for legacy parameters that may have been deprecated or moved to new configuration namespaces during the transition. Effective troubleshooting during an upgrade requires a granular review of component logs, as these files will reflect the specific failures during initialization or internal service connectivity. When a component fails to start after an upgrade, you should systematically audit the configuration files for syntax errors or mismatches caused by the new software version. It is common to encounter issues where a configuration parameter that was once optional becomes required, or where a file path has changed to align with more recent security guidelines. By analyzing the installation logs and the specific component debug logs, you can usually isolate the point of failure, whether it pertains to SSL, TLS certificate binding, network port exhaustion, or database connectivity timeouts. Always verify that your service accounts possess the necessary permissions to access the updated binaries and modify the required registry keys or file system locations. Maintaining a checklist of these specific post-upgrade verification actions is an excellent way to ensure your environment recovers as intended after the software transition is complete. See you in the next lecture. Welcome back to our exploration of CyberArk operations. Today, we are centering our discussion on the intricacies of certificate lifecycle management and token rotation to ensure long-term stability. In any enterprise-grade deployment, the security of connection links relies heavily on the integrity of cryptographic credentials. When we talk about component authentication, we are referring to the underlying trust relationship between the vault, the central policy manager, and the various gateway components. If these authentication files expire or become desynchronized, the entire privileged access management ecosystem experiences a communication breakdown. We often see these issues manifesting as cryptic errors during session initiation or administrative task execution. Consequently, the rotation process itself must be treated as a deterministic procedure rather than an ad hoc recovery effort. By utilizing the automated tools provided by the CyberArk suite, we minimize the human margin of error inherent in manual certificate generation. When we pivot to secure socket layer certificate renewal, the focus shifts toward the web-facing infrastructure, including the password vault web access and the various session managers. Each of these endpoints mandates a verifiable identity chain, which links back to your internal or external trusted root authorities. Updating these configurations is not just about replacing a file. It requires a systematic approach to ensure that the updated public keys match the expectations of the client-side browser or service. Failure to update the trust chain across your distributed servers will lead to blocked connections, which are notoriously difficult to debug once they occur. You must view the distribution of these root certificates as a fundamental prerequisite for successful intercomponent integration. Consistency across the load-balanced web environment is non-negotiable for high availability. Managing the lifecycle of these assets requires a proactive stance, specifically through the creation of an expiration matrix. I find that when we rely on reactive measures, we inevitably encounter service disruptions during periods of high demand. By documenting all certificate and token expiration dates in a centralized tracking mechanism, administrators can proactively schedule rotation windows that align with standard maintenance cycles. You should always aim to complete these rotations well before the hard deadline to account for potential anomalies in the environment. If you encounter a situation where an invalid credential error persists, start by verifying that the newly generated token has propagated to all necessary nodes. Troubleshooting these blocks requires a disciplined examination of the component logs to identify which specific link in the authentication chain is failing. To avoid being caught off guard by these issues, establish a formal schedule for your token rotations. Automation utilities within the CyberArk platform allow for the systematic replacement of these credentials, which drastically reduces the burden on the administration team. When you do perform these updates, ensure that you are validating the connectivity between the vault and the satellite components immediately following the rotation. It is easy to overlook a single gateway that may be sitting behind a different firewall or subnet, but that single oversight can break the global orchestration of your privileged sessions. Treat your cryptographic infrastructure as a living system that requires routine maintenance, not just a one-time configuration step. Effective governance of these life cycles is what separates a stable, resilient installation from one characterized by frequent, preventable outages. See you in our next session. Welcome back. In this chapter, we will focus on maintaining the operational efficiency and performance of the Digital Vault database through strategic index maintenance and resource optimization. Managing a digital vault requires a nuanced understanding of how the underlying database handles data retrieval and storage over time. As administrative activities such as password rotations or account-safe deletions accumulate, the database structures can experience fragmentation, leading to less efficient query execution. When we talk about database optimization, we are primarily addressing the physical arrangement of data on disk and the corresponding index structures that allow the vault to locate specific records quickly. You should view the database as a living system where internal metadata blockages or lock contentions can arise if the indexes are not regularly maintained. By executing standard indexing routines, you ensure that the search path for any given credential or configuration object remains as short and predictable as possible. This is not merely about maintenance. It is about preserving the core performance metrics that the vault relies upon during high-load scenarios. Without a disciplined approach to these background tasks, you may observe degradation in the speed at which password rotation policies are enforced or how quickly session recordings are indexed. Beyond simple maintenance, we must consider the storage utilization parameters that govern how the vault consumes disk space. When you perform massive account-safe deletion projects, the database does not automatically shrink or recover that space in a way that minimizes fragmentation unless specific maintenance routines are triggered. Effectively managing database table sizes involves tracking their growth trajectories against the available hardware capacity, ensuring that historical transaction logging does not expand beyond the bounds of your storage allocation. You need to monitor how the internal cache metrics interact with your index performance, as poorly tuned cache parameters often disguise themselves as disk latency or hardware bottlenecks. When an index becomes fragmented, the overhead of reading data pages increases, which places an unnecessary burden on the I/O subsystem and potentially manifests as slow query execution times. Regularly reviewing performance logs is the best objective method for identifying these trends early before they manifest as systemic instability. By reclaiming storage space proactively and keeping index structures healthy, you provide the vault with the necessary foundation to maintain stability under the unpredictable stresses of enterprise production environments. See you in the next lecture. Welcome back to our discussion on maintaining the operational integrity of the CyberArk platform. In this session, we focus on system monitoring and health reporting, ensuring your infrastructure remains both performant and verifiable. To maintain the operational stability of a privileged access management environment, you must implement a robust health monitoring framework that bridges the gap between infrastructure metrics and security visibility. Monitoring effectively starts with observability, where you track component statuses, memory consumption, and disk volume levels across all tiers of your architecture. When we talk about disk exhaustion, we are not simply referring to log files, but the critical space required for vault metadata, session recording storage, and database transaction logs. If these volumes reach a critical threshold, the CyberArk services may experience a sudden halt, leading to significant business disruption. Therefore, you should establish automated capacity tracking to alert administrators well before any operational boundary is reached. By integrating these metrics into your existing enterprise management systems, you move from a reactive posture, where you fix things after they break, to a proactive one, where you manage trends before they become incidents. Simple network management protocol and syslog serve as the primary conduits for event routing and alert tracking in this context. You need to configure the digital vault and its associated components, such as the central policy manager and privileged session manager, to forward system events to your centralized event management platform. This isn't just about security events. It involves capturing health-specific signals like service state transitions, high CPU utilization, or network latency spikes. When a component enters an error state, the integration should trigger an alert that provides enough context for an administrator to act immediately. By standardizing the format of these logs, typically through syslog, you enable the automated parsing of alerts, which is essential for reducing the mean time to repair. Furthermore, this data provides the necessary evidence for compliance auditing, where you must demonstrate that your environment remains within defined performance benchmarks. Generating automated health reports is the final, essential step in verifying the efficacy of your monitoring strategy. These reports should aggregate the raw data collected over specified periods, transforming technical logs into visual graphs that stakeholders and auditors can easily interpret. For instance, a dashboard showing memory processing capacities over the last quarter helps you justify infrastructure upgrades when load trends demonstrate consistent growth. Compliance teams often require periodic validation that the infrastructure is operating as intended, and automated reports serve as the objective proof required for these checks. By conducting these audits regularly, you align your technical operations with broader performance benchmarks established during the initial deployment. Maintaining this level of visibility ensures the platform remains a reliable bedrock for your organization's privileged credentials and sensitive session data. Look forward to seeing you in the next lecture. Welcome back to our technical deep dive into the CyberArk ecosystem. In this session, we are shifting our focus to the Digital Vault's internal diagnostic capabilities, specifically how to parse and interpret the primary informational tracing logs that reside at the heart of your security infrastructure. When we approach log analysis within a hardened CyberArk environment, we are essentially performing an audit of the engine's internal state. The itlog text file is the primary repository for this data, capturing high-frequency events and critical status changes. Understanding the structural codes within these logs is vital, because they translate raw machine output into identifiable patterns, such as database commit failures or transient network drops. If you encounter an authorization failure, the log will often provide a specific return code that acts as a signifier for the underlying authentication mechanism that rejected the request. These identifiers allow an administrator to distinguish between a malformed request, a locked target account, or a genuine breach attempt. By mastering the cadence and syntax of these records, you move away from guessing and toward a structured, evidence-based approach to resolution. To gain this granular level of insight, one must often configure the appropriate trace levels within the DB PAM-SEN file. By setting the diagnostic logging to a more verbose state, you enable the vault to capture the minutiae of application workflows that might otherwise remain opaque. However, this is a delicate balance, as excessive tracing on a production node can introduce resource contention or disk I/O bottlenecks. You want to focus your trace configuration on the specific component that is exhibiting aberrant behavior, such as a failing vault rotation or a stalled service process. Once you have narrowed the scope, tracking the progression from a client request to the subsequent database processing cycle becomes the primary method for mapping system events across a timeline. This temporal correlation is essential when you are trying to reconstruct a chain of events following a sudden engine shutdown or an unexpected service heartbeat failure. Analyzing these files manually can be a daunting task, especially when dealing with massive entries that span thousands of lines of output. Professional troubleshooting requires utilizing standard log analytics utilities, such as grep, awk, or dedicated log parsers, to filter through the noise and extract specific error sequences. When you are looking for evidence of resource depletion, look for timestamped entries that indicate waiting threads or locked database tables. which are classic indicators of contention. Effective analysis involves comparing these extracted error sequences against known patterns found in the official documentation or your internal history of incidents. By archiving past log fragments and automating the search for specific failure indicators, you create a baseline for what normal operation looks like in your specific deployment. The goal of this process is to transform unstructured diagnostic data into actionable intelligence that minimizes the mean time to repair for your critical components. Whether you are dealing with a recurring network timeout or an elusive synchronization error, the structural integrity of the IDA log serves as your primary diagnostic truth. Consistently monitoring the output of these logs, even during periods of stability, helps train your eye to detect subtle shifts in the vault's operational health. This rigorous practice ensures that when a genuine failure occurs, your incident response will be guided by established patterns rather than trial and error debugging. I encourage you to spend time in a lab environment forcing error conditions to see how they manifest in the traces, as this prepares you for real-world scenarios. See you in the next lecture. Welcome back. In this lesson, we will focus on the practical application of component tracing log diagnostics to maintain and debug your CyberArk infrastructure. When we discuss the health of a distributed PAM environment, we are essentially talking about the flow of data across various architectural boundaries. The CyberArk components like the Password Vault Web Access, the Central Policy Manager, and the Privileged Session Manager all operate as discrete nodes that rely on precise synchronization. Tracing across these components requires a disciplined approach to log analysis, where we correlate events by timestamps and transaction IDs to reconstruct the lifecycle of a user request. If a user experiences an issue with the web interface, for instance, the error might originate in a misconfigured web config file or a framework fault that remains invisible until you increase the logging granularity. By moving beyond simple event logs and into advanced tracing, you gain the visibility required to map the internal state changes of the policy engine as it interacts with target systems. The policy engine, specifically the Central Policy Manager, relies on detailed logs to describe the phases of connection and prompt matching. When a password rotation fails, the console logs serve as our primary source of truth, detailing whether the failure occurred during the authentication phase or if the engine stalled while esperando for a specific prompt from the target device. You should look for discrepancies in the expected state machine versus the actual output captured in these diagnostics. Similarly, the Privileged Session Manager recording logs are vital when you observe session launch drops or video encoding irregularities. These logs reveal whether the bottleneck resides at the gateway level, perhaps due to resource exhaustion or a failure in the protocol translation layer. By identifying where the session handoff fails, you narrow down the root cause from a systemic issue to a specific configuration gap within the connection component. Correlating these component trace logs with the digital vault logs is the final essential step in understanding an end-to-end transaction sequence. The vault acts as the anchor point, and any request originating from the web interface or the policy engine must be authenticated and authorized through the vault's own query logs. When you see a request arrive at the Password Vault web access but fail to manifest as a record in the vault's logs, you know immediately that the obstruction exists in the network layer or the web application's communication bridge. Keeping these logs synchronized through centralized time sources like NTP is non-negotiable for effective correlation. It is often productive to analyze the sequence of events from the vault's perspective first, then work outwards toward the edge components to see where the request chain is interrupted or diverted. However, we must address the operational reality that advanced tracing is inherently resource-intensive and can lead to storage exhaustion if left in a verbose state for too long. You should treat high-level tracing as a temporary diagnostic toggle rather than a permanent operational baseline. Once the root cause of a connection failure or a session recording drop is identified and rectified, it is imperative to roll back to standard logging levels to preserve disk space and maintain the performance integrity of the host server. Failure to revert these settings will eventually result in the log volumes hitting their capacity limits, which can paradoxically cause the components themselves to freeze or behave unpredictably under pressure. Always maintain a checklist that includes resetting these parameters alongside your remediation steps to ensure that your diagnostic efforts do not inadvertently introduce a secondary failure. See you in the next lecture. Hello. Welcome back to our discussion on navigating the intricacies of the CyberArk infrastructure. In this section, we shift our focus toward the architectural integrity of our network pathways and how to maintain the stability of the core vault connection. We will examine the specific diagnostic methodologies required to identify and resolve communication failures between distributed components and the secure vault endpoint. When troubleshooting connectivity between a remote component, such as a credential provider or a session manager, and the central vault, the first step is often to move beyond simple ping tests. While ICMP reaches might verify that the server is online, it tells us nothing about the health of the specific application layer traffic that CyberArk relies upon. We should prioritize using utilities like PowerShell's testnet connection or traditional tools like Telnet to verify that specific ports are indeed open and listening. You must confirm that the pathway between the component and the vault is traversable for the specific TCP ports required, which are typically 1858 for standard vault communications. If these connection attempts fail, we must look deeper into the stateful tracking behaviors of the intermediate network infrastructure. Often, firewalls may appear correctly configured at a high level, but might be dropping packets due to session timeout mismatches or packet fragmentation issues that are invisible to basic connectivity checks. Stateful inspection firewalls frequently create roadblocks for long-lived connections, which are characteristic of CyberArk component communication. If a firewall silently drops an idle connection because it perceives the session as inactive, the component will suddenly find its link to the vault severed without a clear error message. In these scenarios, examining the firewall logs specifically for blocked traffic streams is the only way to gain clarity on why the TCP handshake is failing at the perimeter. You should also consider the impact of network address translation, or NAT, in multi-site deployments where virtual routing distortions can lead to asymmetrical routing patterns. If the return traffic from the vault reaches the component through a different path than the outbound request, the security devices along that path are likely to drop the packets as invalid. Validating the routing consistency across your multi-site infrastructure is foundational to ensuring that these persistent connections remain stable over long durations. Beyond Layer 4 connectivity, we frequently encounter issues rooted in the TLS handshake process, typically manifested as certificate trust validation failures or cipher suite mismatches. When a component attempts to connect to the vault, it performs a cryptographic exchange that requires both sides to agree on a compatible cipher configuration and verify the server's identity. If the vault certificate has been rotated but the component's trust store is not updated, the handshake will be rejected immediately during the validation phase. This is often accompanied by entries in the component logs indicating that the certificate is not trusted or has expired. You should audit the registry configuration or the local certificate store of the component to ensure that the proper root and intermediate certificates are correctly imported. When dealing with complex environments, using OpenSSL command line tools can help you inspect the specific certificate chain being presented to ensure it matches the requirements expected by the CyberArk software. Finally, we must address the strategy of implementing redundant routing for our critical privileged access management infrastructure. Relying on a single path to the vault is a significant risk, particularly in high availability setups, where the failure of a single router or switch shouldn't result in a total management blackout. By implementing redundant routing, we create layers of failover capability that allow traffic to automatically reroute in the event of an infrastructure link failure. However, you must test these paths under load to ensure that the rerouting does not introduce latency spikes that could cause the vault to time out a waiting session. Consistent monitoring of these pathways allows you to proactively identify bottlenecks before they affect the end-user experience or the security of your privileged accounts. Ensuring that these components can reliably communicate with the vault is not just a networking task, but a vital part of your overall security governance. I will see you in the next lecture. Welcome back. In this session, we will examine the mechanisms behind password reconciliation failures and the systematic approach required to restore synchronization between your managed accounts and target systems. When an automated credential rotation fails, the central policy manager immediately attempts to trigger a reconciliation process to restore access. Investigating these failures requires a disciplined look at the target execution platform, as many errors are rooted in simple connectivity drops or network timeouts. You should begin by isolating whether the error is persistent across the entire platform or specific to a subset of accounts. Analyze the policy engine error strings carefully, as they often contain specific status codes provided by the target operating system. For example, a generic access denied code might mask a more subtle misconfiguration, such as an expired reconciliation account password or a disabled service account on the target machine. By scrutinizing these logs, you move from guessing to verified diagnostics, which is the hallmark of a functional security architecture. A common pitfall is ignoring the elevation permissions required by the reconciliation account itself. This account must have sufficient privileges, often administrative or root level, to modify credentials on the target system without triggering security alerts or policy blocks. You must verify that the target system configuration parameter alignments match what the platform expects, particularly concerning password complexity rules or age restrictions that might block a change request. If the reconciliation account lacks the necessary rights to perform the password update, the policy engine will return a failure despite the account having otherwise valid credentials. You should also check for account locking flags on the target, as continuous failed attempts often lead to a hard lockout state. Resolving this requires you to manually unlock the account before the automated process can regain control and resume its intended function. Testing interactive login sequences remains the most effective way to validate your plugins and platform behaviors. By tracking execution step behaviors through terminal simulation logs, you can observe exactly where the automation flow diverges from reality. If the system expects a specific prompt that the target does not provide, the plugin will invariably fail due to a synchronization mismatch. You may need to adjust the delay parameters or the expect SYN patterns within the platform configuration to accommodate slower network response times or varying banner messages. Synchronizing the local database caches of the vault with the active values on the target is essential for maintaining consistency. When the vault believes a password is in one state while the target has another, your only option is often to force a reconciliation or manual reset. Finally, you should focus on optimizing retry intervals and platform parameters to minimize the risk of continuous lockouts on sensitive target nodes. If the retry policy is too aggressive, you risk locking out an account repeatedly, which creates a self-inflicted denial of service condition. Evaluate the jitter and sleep values within the platform policies to ensure that the policy engine behaves gracefully under load or during intermittent network instability. Consider the environment's topology when setting these timeouts, as distributed systems often have higher baseline latency than local infrastructure. Maintaining alignment between the vault, the CPM, and the target platforms is an exercise in managing state, and these failures are best viewed as feedback regarding your environment's health rather than mere system errors. Through careful log analysis and step-by-step verification, you can turn these episodes into opportunities to harden your entire privileged access management implementation. I will see you in the next session. Welcome back. In this chapter, we explore the complexities of session recording storage diagnostics to ensure your audit trails remain intact and accessible. When troubleshooting issues within the session recording pipeline, we must first focus on the journey of the recording from the privileged session manager to the vault. Upload failures often stem from misconfigurations in the underlying storage paths or incorrect file system permissions assigned to the service account responsible for handling these buffers. If the session manager cannot write the raw media files to the landing zone, the entire chain breaks, leading to missing audit data. It is imperative to verify that the storage paths are properly mounted and that the service operating the session recording service has explicit write access to these directories. Without these permissions, the binary data remains stuck in the temporary buffers on the session manager server, which will eventually lead to space exhaustion on the component itself. You should always validate these folder paths in the configuration against the actual operating system ACLs to confirm that nothing was modified during recent hardening or server updates. By ensuring the handshake between the session manager and the storage target is seamless, you eliminate the most common point of failure in the recording lifecycle. Beyond simple connectivity, we frequently encounter latency issues caused by backlogged background transition tasks. The privileged session manager relies on internal processes to move, compress, and finalize recordings before they are fully ingested by the vault for long-term retention. When these tasks queue up, it is usually an indicator of resource contention or an accumulation of unprocessed files that have overwhelmed the worker threads. Reviewing the component logs, specifically focusing on the transition service, allows us to identify if the engine is struggling to keep up with the volume of concurrent sessions. If you find high queue congestion, you might need to adjust the frequency or concurrency settings to balance the load more effectively. It is common to see these delays manifest as missing recordings in the web interface, as the file has not yet been processed through the rendering pipeline. Carefully analyzing these logs helps distinguish between a permanent failure and a temporary bottleneck caused by intense system activity or insufficient processing throughput during peak hours. If users report that they cannot play back recordings via the web interface, we must differentiate between storage-level errors and rendering failures. Sometimes the raw media file is safely stored, but the metadata or the indexing service responsible for the web viewer has become desynchronized. This corruption or failure in the rendering stack often manifests as a spinning loading indicator or an error message indicating that the file is unavailable. In such cases, checking the indexing logs helps determine if the system successfully mapped the recording to the corresponding session ID. If re-indexing is required, the metadata service must be triggered to scan the storage archives and reconstruct the necessary links between the database entries and the physical files on disk. Following this, if the file remains inaccessible, deep diagnostics on the playback service itself are warranted to ensure that the browser-based player can negotiate the correct codec with the underlying storage layer. Finally, we must address the lifecycle management of these recordings, particularly the risk of storage quota exhaustion. As the volume of privileged activity grows, the storage allocated to session recordings will inevitably fill up, requiring robust automated archiving and data relocation routines. If these automated workflows fail, the session manager may enter a protective state where it stops recording altogether to prevent file corruption. Configuring proper storage thresholds ensures that when the system hits a high water mark, older data is moved to cheaper secondary storage or archived off-platform. Monitoring this capacity is not merely a disk space exercise, but a critical component of maintaining audit compliance and ensuring that the vault remains performant. By proactively managing the relocation of historical files, you maintain the integrity of the audit trail and avoid the abrupt cessation of recording services which could leave your organization vulnerable. I will see you in the next lecture. Welcome back. In this lecture, we will explore the methodologies for optimizing resource allocation and performance tuning within a CyberArk environment, focusing on distributed system stability. Performance tuning in a distributed privileged access management architecture is rarely about singular, magical configuration changes. Instead, it requires a systemic approach to identifying where resource contention resides, whether that be in the Vault database, the central policy manager, or the individual session manager nodes. When we look at concurrency, we must examine the session capacity limits configured on the session manager servers. By default, these servers are tuned for general-purpose workloads. But in high-velocity environments, you might need to adjust task concurrent threads to prevent resource starvation. It is essential to monitor memory usage thresholds and web application pool recycle schedules carefully. Aggressive recycling can introduce latency, while infrequent recycling may lead to memory bloat, eventually degrading the responsiveness of the web interface. You need to identify what your specific infrastructure can handle by performing actual load tests until you reach the breaking point of your current hardware configuration. Once you establish these breaking point boundaries, you can derive realistic capacity planning metrics that govern when to scale out rather than up. Documenting these performance baselines is not merely an administrative chore. It serves as the operational guide when performance begins to drift during peak audit or rotation windows. The policy engine often represents the most significant load on the digital vault, particularly during large-scale credential rotation or automated account discovery scans. If these operations are not synchronized, you can inadvertently overwhelm the database, leading to slow query responses that affect all other users. We address this by tuning the search parameters and the polling intervals within the policy configuration files to spread the workload more evenly. It is beneficial to analyze the database query logs to see which specific operations are consuming the most cycles during your discovery phase. By adjusting the frequency of these operations and ensuring that they are scheduled during off-peak hours, you effectively reduce the immediate pressure on the vault. Remember that every adjustment to the policy engine search depth or frequency has a direct correlation to the responsiveness of the end-user GUI. When the database is locked or heavily occupied with discovery updates, the vault becomes sluggish. which is a symptom that optimization is required at the query logic level. Always validate your changes in a staging environment that mirrors your production load to ensure that you do not inadvertently break existing automated process timers or account rotation workflows. Effective optimization depends on maintaining a clear understanding of the hardware limits associated with your virtualization or bare metal environment. You should look at the CPU and RAM distribution for each component, ensuring that the session manager servers, for instance, have enough headroom to handle encrypted stream processing without dropping packets. If you are noticing packet loss or jitter in privileged sessions, the bottleneck is often found at the intersection of network bandwidth and local resource availability on the gateway node. Tuning these parameters is an iterative process that begins with defining your baseline performance metrics during normal business hours. Compare these metrics against the behavior observed during high utilization periods to pinpoint exactly which configuration handles the load poorly. Never make multiple changes simultaneously, as this makes it impossible to determine which adjustment resolved the latency or which one introduced a new performance regression. By documenting every single change in your operational templates, you create a feedback loop that stabilizes the system over the long term. This systematic governance ensures that the performance tuning process is repeatable, predictable, and fully integrated into your existing lifecycle management for the PAM platform. Talk to you later. Welcome to our exploration of dual control workflow architecture, where we will examine the mechanisms required to secure highly sensitive privileged credentials. We will focus on the architectural design patterns necessary to enforce strict operational oversight and maintain non-repudiation in your environment. In any robust privileged access management deployment, the concept of dual control is not merely a feature, but a foundational security requirement for high-risk assets. At its core, this architecture ensures that no single individual possesses the unilateral authority to access or manage critical credentials, thereby mitigating the risk of insider threats or human error. When you configure dual control, you are effectively creating a logical gate between the requester and the target system, which requires an explicit second layer of administrative approval. The technical implementation within the CyberArk Vault relies heavily on defining specific platform parameters that dictate how requests are initiated, routed to authorized confirmers, and eventually fulfilled. By mapping these approval routing paths to specific user groups, you establish a chain of custody that is both visible and auditable within the system logs. This multi-layer approach forces a separation of duties, ensuring that those requesting access cannot also be the individuals granting the authorization. Managing these workflows requires a precise configuration of account-level or platform-level dual control settings, which can be tailored to suit the risk profile of the target system. When you define a safe, you must decide how these rules propagate and interact with the existing user permissions to ensure that operational speed does not completely supersede security constraints. It is quite common for architects to struggle with the nuances of request expiration, as failing to appropriately size the validity period of an approval can lead to significant friction in production environments. If a request expires before the user acts upon it, or if multiple request collisions occur within the same safe, you need to understand how the vault handles these logical conflicts. A well-designed workflow accounts for these edge cases by providing clear feedback mechanisms that help users understand why their request was denied or why it may have timed out prematurely. Ultimately, the stability of your dual control implementation depends on your ability to balance these constraints against the real-world needs of your privileged users. One of the most critical aspects of this architecture is the design of break glass or emergency exception paths that allow for bypasses during catastrophic system failures. While these paths are necessary for operational continuity, they represent a significant security risk that must be strictly governed and monitored with extreme vigilance. You should design these emergency paths so that they are effectively siloed from general access, perhaps requiring an out-of-band notification or a hardware-based authentication token to activate. All activity occurring within these emergency sessions must trigger enhanced logging, ensuring that the audit trail captures not just the usage of the account, but the context of the emergency itself. Because these exceptions are so powerful, they often include additional layers of non-repudiation, such as requiring manual sign-off after the event to verify that the breach of protocol was warranted. When you properly balance these strict security enforcements with the practical reality of maintaining uptime, You achieve a level of maturity that satisfies even the most rigorous compliance auditors. Auditing is the final, non-negotiable component of any dual control strategy, as it provides the evidence required to verify that the workflow was honored in every instance. The Vault automatically generates transaction histories that track the lifecycle of a request from the moment of initiation through the approval phase, and finally to the actual credential retrieval. These audit histories act as a ledger, ensuring that each interaction is cryptographically tied to a specific identity, which is essential for maintaining non-repudiation. When you perform troubleshooting, you will often find yourself digging into these logs to determine exactly where a confirmation delivery failed or why a notification did not reach the intended approver. By treating these logs as primary sources of diagnostic truth, you can optimize your workflows and ensure that the delivery of authorization requests is both reliable and predictable. Consistently reviewing these histories allows you to refine your permission models and adapt your dual control posture as the organization grows and its threat landscape evolves. I look forward to discussing how these concepts interface with our broader policy management strategies in the next lecture.